On the morning of 18 November 2025, solar observatories tracking 3I Atlas reported a shift that did not match any projected models. The object had been expected to follow a predictable curve as it skimmed the inner region of the Sun's magnetic influence, a path refined over weeks of observation. Instead, a set of coordinated instruments detected a deviation in both its apparent position and its reflective profile. The change was subtle at first, almost buried beneath normal solar interference, but the time-stamped data aligned too precisely to be dismissed. Something had altered the object's behaviour at the moment when the Sun's influence should have been at its strongest and most constraining. For researchers who have followed 3I Atlas since it entered measurable range, the anomaly did not present itself as a dramatic turn or explosive event. It emerged as a small mathematical inconsistency, a shift in its velocity vector that resisted all familiar explanations. Natural forces near the Sun are powerful, but they are also well modelled, leaving little room for spontaneous irregularities. Yet this object moved as if responding to a separate, unaccounted-for influence. Instruments recording its thermal signature noted an unexpected stabilization, rather than the sharp rise anticipated at such close proximity. And its dust output, which had been minimal for weeks, remained almost non-existent even under extreme irradiation. Every measurement pointed toward a behavior no one had forecast. Teams reviewing the early data have remained cautious, aware that solar proximal observations are vulnerable to distortions. Still, the consistency of the readings from independent observatories indicated something tangible. The anomaly was small, deliberate, and timed so precisely with its closest approach that it forced researchers to reassess all earlier assumptions about the object's structure and its response to solar conditions. As data continues to unfold in real time, the central question becomes unavoidable. What exactly happened to 3I Atlas when it crossed that narrow region of space where natural forces should have left no room for surprises? And this is where the story begins to deepen. The approach of 3I Atlas toward the Sun was never expected to be simple, but it was supposed to be predictable. By mid-November, astronomers had refined its path using a combination of optical tracking, infrared measurements, and gravitational modelling. Each data set pointed toward a clean, steady descent into the inner solar region, where the Sun's radiation, its uneven magnetic contours, and its tidal forces typically dominate the behaviour of any interstellar visitor. For weeks, the trajectory held firm. Nothing in the early models suggested an approaching disruption, yet as the object drew closer, the details of its motion revealed an underlying tension between expectation and reality, a slow accumulation of small deviations that only now, in hindsight, appear as the early hints of the event that unfolded days later. The Sun exerts more than just gravity on a passing body. Its pressure, its magnetic field, and its plasma outflows act together in a dynamic and often chaotic environment. Most objects entering this region produce recognizable signatures. Ice sublimates, dust escapes. Jets form where surface materials break down under intense heat. These processes typically create slight irregularities in motion, but they fall within predicted ranges. With 3I Atlas, none of these mechanisms behaved as anticipated. As it traced its arc inward, astronomers waited for its first sustained release of dust or vapour, the kind that would confirm the presence of volatile materials beneath its surface. Instead, instruments recorded a persistent absence of outgassing. Even as temperatures rose to levels that should have cracked open any icy body of its size, the object remained quiet. This silence was not initially interpreted as an anomaly. Some interstellar bodies contain little volatile material, making them less reactive to solar heating. The more intriguing detail came from the stability of its reflective profile. As sunlight intensified, 3I Atlas's albedo should have shifted, revealing fractures, shedding surfaces, or growing brightness variations as different materials responded unevenly to heat. But its reflectivity remained nearly unchanged. The surface appeared steady, almost indifferent to the rising radiation. When the team compared these readings with observations taken weeks earlier, they found only marginal differences, far too small for an object experiencing such conditions. It was as though the surface resisted thermal transformation, behaving more like a cohesive structure than a fragile mixed composition body. As the approach continued, researchers monitoring its rotational state began noticing something equally unusual. The rotation of an interstellar object is rarely stable near the Sun. Jets, dust release, and thermal stress all produce torque, altering the spin rate and orientation. But 3I Atlas maintained a remarkably consistent rotation period. Small fluctuations appeared, but they lacked the magnitude expected at this distance. This raised an early question within the observational teams. Was 3I Atlas structurally different from known comet-like bodies, or was it undergoing internal processes not yet understood? The question gained weight as the object's proximity increased and its path remained cleaner than any prediction allowed. The Sun's gravitational gradient grows steep near perihelion. The closer an object falls, the more sensitive it becomes to even slight perturbations. The models that scientists used to track 3I Atlas incorporated these effects with precision. Yet in the final days before the deviation, the predictions began to drift by small margins. They were tiny at first, fractions of a second in arrival times, minute discrepancies in projected coordinates. Analysts attributed most of these to observational error, a common challenge near the Sun where light scattering and turbulence distort data. But the corrections applied to compensate for those distortions did not fully remove the inconsistencies. Each new dataset required slightly more adjustment than the one before it. Understanding the solar environment is crucial to grasping why this mattered. The Sun's influence forms a gradient of forces that overlap and interfere with one another. Radiation pressure pushes outward, plasma flows create drag, and the magnetic field fluctuates in patterns that affect charged particles and conductive materials. A natural object drifting through this environment should show a chaotic but interpretable response. But the movement of 3I Atlas grew cleaner instead of more erratic, smoothing into a pattern that looked almost guided. The line of its approach tightened, and the expected random deviations became nearly absent. Observers monitoring the motion noted that the path settled into an unnaturally stable curve, as though something internal or external counterbalanced the forces acting upon it. Just after the midpoint of its inward descent, the thermal instruments detected a curious phenomenon. The rate of temperature increase began to slow. The Sun's radiation, which intensifies dramatically with proximity, should have pushed the thermal signature upward at an accelerating rate. Instead, the increase flattened. Not only did the surface appear resistant to sudden heating, but the object's overall thermal profile suggested a form of redistribution. Heat absorbed in one region appeared to dissipate across its surface faster than expected. This behavior reinforced the growing suspicion that 3I Atlas was not simply a porous structure of ice and dust. Something within its composition changed the way it interacted with energy. At this stage, the team working with solar coronagraph data decided to cross-reference their findings with heliophysics instruments orbiting at different angles. The goal was to determine whether the early inconsistencies were a simple observational artifact or the beginning of an anomaly. Data pulled from both near-Earth orbit and a solar orbiting probe confirmed that the coordinates matched within an unusually tight range. In other words, the inconsistencies were not noise, they were real. And despite deeper verification, no known solar process explained the stability of the object's motion. By the time 3I Atlas reached the boundary where solar forces would be expected to dictate every detail of its behavior, the object remained solidly within its projected corridor. Yet the corridor itself was shifting. The predictions needed constant refinement, each update pushing the future positions slightly away from the earlier projection. It was not enough to draw attention on its own, but close inspection revealed a pattern. The small deviations aligned in a specific direction rather than scattering randomly. This directional bias hinted at an underlying mechanism. Something exerted a subtle but continuous influence on the trajectory, and it was not part of any natural model. In the final stretch before its closest approach, the Sun's magnetic field should have begun to interact more aggressively with surface materials. Measuring these interactions allows astronomers to classify whether an object contains metals, silicates, or mixed compounds. The expected fluctuations did appear, but they emerged in a pattern too orderly for a loosely bound body. Instead of a messy interplay of charged particles, the readings displayed a repeating structure, small pulses that appeared almost rhythmic. At first, these pulses were dismissed as an artifact from the instrument, but when a second observatory reported the same pattern, separated by thousands of kilometers and using different equipment, the possibility of a structural or compositional anomaly became unavoidable. As 3 Atlas entered the region, where solar radiation normally tears apart fragile interstellar visitors, imaging instruments expected to capture signs of degradation. Edges soften, loose fragments escape, layers peel away. But none of this appeared. Instead, the silhouette sharpened. With rising illumination, what should have blurred into a diffuse glow resolved into a shape with unexpectedly coherent contours. The object maintained clarity, even as it swung into regions where light scattering typically overwhelms detail. Researchers later noted that the stability of those contours remained one of the most confounding elements of the approach. With each passing hour, the approach of 3I Atlas forced scientists to confront the idea that the object's solar behaviour would not mirror the known patterns catalogued in previous interstellar objects. There was no surge in outgassing. There was no collapse of structure under thermal stress. Its motion remained cleaner than any projection allowed, as though the object moved through the inner solar region with a degree of self-consistency foreign to natural bodies. By the time it reached the critical region near the Sun, the patterns had become impossible to ignore. The predictions were still functional, but something beneath them had shifted. The object's expected reactions to solar forces failed to materialize, and the data converged on one unavoidable conclusion. 3I Atlas was about to do something no model could confidently describe. And yet even this growing list of irregularities did not prepare researchers for the precise moment when the behavior changed. That shift would occur in the hours ahead, marking a departure from every natural object known to move this close to the Sun. But to understand the significance of that event, the details of the first detection require closer examination. When the deviation was first detected, no one recognized it as a deviation at all. It emerged as discrepancy buried inside a routine data transfer window, the kind that researchers usually resolve by adjusting calibration parameters. A solar observatory positioned at a trailing orbit had been collecting readings from multiple channels: optical, infrared, magnetometric and radiative flux sensors. Each of these instruments carried its own margin of uncertainty, especially this close to the Sun where scattering, flare activity, and charged particle interference distort nearly everything. Yet on that morning, 3 separate channels displayed the same microscopic irregularity, a shift in the object's apparent position that exceeded the expected error by a small, stubborn margin. At first, analysts flagged the data as likely noise. Observing near the solar limb is notoriously complex because the brightness gradient forces instruments to rely on post-processing algorithms to distinguish faint targets from background turbulence. For a time, the discrepancy sat unexamined, waiting for the next batch of telemetry to either confirm or contradict it. When the next cycle arrived, the shift reappeared. This time the offset was slightly larger, and more importantly, it emerged at nearly the same timestamp across 2 independent observatories. That timing alignment signaled that the anomaly could not be dismissed casually. Noise rarely synchronizes across systems separated by millions of kilometers. Something in the behavior of 3I Atlas had altered just enough to trip the boundary between expected and unmodeled motion. The next step involved checking the instruments themselves. Technicians reviewed the calibration logs, sensor temperatures, and error correction parameters, searching for a mechanical or computational explanation. None appeared. The detectors were running within optimal ranges. No recent radiation spike had overwhelmed the processors. Even the attitude control systems of the observatories showed no irregularities. With instrument error ruled unlikely, attention shifted back to the object and its interactions with the Sun. The small displacement might have been caused by an outgassing jet, but the spectral channels that monitor gas release remained silent. Infrared sensors showed no sudden temperature spike that would accompany surface cracking. The anomaly remained an unresolved point in the dataset. To make sense of it, analysts compared the suspected deviation with historical cases of cometary motion near the Sun. Comets often display erratic acceleration when internal pressure forces material outward along fractures. These events usually produce temperature signatures, brightness flares, or tail instabilities. In this case, none of those markers were present. The silhouette of 3I Atlas preserved the same compact shape it had held for days. Its surface reflectivity remained steady. Its thermal gradient continued rising much more slowly than expected. If any forces acted upon it strongly enough to alter its trajectory, they left no conventional trace in the measurements. That absence set this deviation apart from typical solar proximal behaviour. Instead of a burst of activity, the data showed a quiet, precise displacement, a movement with no accompanying noise. The next irregularity surfaced when analysts examined the object's radial velocity. Using Doppler shift measurements, they compared its speed with predicted values from orbital models. The difference was extremely small, but persistent. The object was moving fractionally faster than the model projected, though the increase was so minor that it could easily have been overlooked without the positional anomaly to draw attention to it. What mattered was the consistency. The acceleration was not random. It matched a smooth curve that had no basis in solar dynamics. Typically, solar radiation pressure can accelerate dust and lightweight fragments, but the massive 3-eye atlas, based on earlier estimates, was far too large to experience such a clean and sustained effect. Something other than radiation, gravity, or outgassing appeared to exert influence over its path. To verify the details, teams brought in data from a probe orbiting closer to the Sun. This probe uses coronagraph imaging to block out the Sun's blinding light, revealing faint structures around it. When researchers overlaid the probe's imaging results with optical datasets from more distant observatories, they found alignment down to a precision rarely achievable near the Sun. The anomaly persisted across these independent lines of observation. What had begun as a statistical irregularity now looked like a measurable shift in the object's motion. The instrument teams then examined the object's electromagnetic signature. Objects moving through the Sun's magnetic field generate subtle interactions that can be detected as fluctuations in charged particles or anomalies in polarized light. The measurements from 3-eye atlas revealed something unexpected, a faint, repeating fluctuation pattern. It did not resemble signals produced by plasma jets or rotational fragmentation. Instead, it appeared as a sequence of consistent pulses, tiny, rhythmic variations that repeated over intervals too regular for natural solar interference. The pulses were faint enough that they might have gone unnoticed in a less scrutinized context, but paired with the positional irregularity, they gained new significance. Researchers looked for known natural mechanisms that could explain these pulses. Rotational modulation can produce periodic changes if the object has bright and dark regions that pass through the line of sight. But the pulses were not tied to brightness variations. Their timing also failed to match the measured rotation period. That mismatch suggested that the source of the pulses was neither surface albedo nor rotation driven. If the pulses originated within the object, their consistency hinted at internal structure or composition, with properties not found in typical interstellar debris. The investigation expanded to the object's thermal emission. High-resolution thermal readings indicated that heat was spreading across the surface unusually quickly, suggesting a material with high thermal conductivity, far higher than expected for ice, porous rock, or carbonaceous compounds. This efficient redistribution of heat could explain why surface cracking or outgassing remained absent. The object appeared capable of diffusing the Sun's heat across its structure, rather than allowing localized stress to build. This level of thermal stability would require a material composition significantly different from what current models assume for interstellar bodies. If the object possessed such properties, it could feasibly remain intact and stable in regions where natural objects begin shedding dust and vapor long before reaching comparable temperatures. The anomaly became clearer when analysts plotted its projected path against the updated measurements. The object's trajectory fell slightly outside the predicted corridor, deviating along a vector that aligned with the earlier fluctuations detected in its electromagnetic signature. The alignment was subtle, but unmistakable. The path of deviation and the rhythm of the fluctuations suggested correlation. If the pulses carried structural or energetic significance, they might have interacted with solar forces in an unexpected way. Analysts proposed several hypotheses. One possibility was an internal redistribution of mass, causing the center of gravity to shift. Another hypothesis involved the object's material interacting with the Sun's magnetic field in a way that altered its motion. This scenario required assumptions about conductivity and structure that pushed beyond known natural materials. The analysis deepened when light curve data revealed another anomaly. When the object rotated, its brightness variation followed a pattern too orderly for a rough, irregular body. Most interstellar objects produce jagged light curves that reflect their uneven surfaces, but 3I Atlas displayed a curve with smooth transitions, suggesting that its surface was either more uniform than expected or composed of materials that reflect light in a coherent manner. This coherence in surface reflection matched the earlier observations of stable contours, reinforcing the idea that the object's structure differed fundamentally from typical comet-like bodies. The next irregularity came from the radiation spectrum analysis. Instruments detected a minor shift in the reflected wavelengths, one that could not be fully explained by thermal emission or solar scattering. The shift implied the presence of a surface layer with optical properties that altered under rising solar pressure. Yet the alteration was extremely slight, suggesting a resilient surface composition resistant to rapid transformation. Because interstellar objects are expected to exhibit complex mixtures of organics and minerals that degrade under solar heating, the stability observed here called for deeper examination. As each dataset was reviewed, the narrative became clearer. The anomaly was not a single event, but an accumulation of interconnected signals. The positional displacement matched the unexpected acceleration. The acceleration connected with the electromagnetic pulses. The pulses linked to a thermal profile that resisted conventional behaviour. And all of these layers combined to outline an object that appeared to maintain internal order despite the harsh environment around it. This constellation of evidence forced scientists to consider something they had not anticipated. 3I Atlas might not only be structurally unusual, but it might also possess a level of physical coherence that allowed it to interact with solar forces in ways beyond current models. Still, caution framed every discussion. Nothing in the data revealed intent or control. The patterns could be the result of exotic materials or unknown internal dynamics, rather than any deliberate mechanism. Yet the precision of the anomaly remained undeniable. As researchers compiled the evidence, they realized that something significant had begun near the Sun, something subtle, measurable, and deeply disruptive to prior assumptions. But even this discovery was only the beginning. The thermal anomaly, once dismissed as a footnote in the dataset, soon revealed a deeper pattern that pointed toward a behavior no one expected. As the Sun's radiation intensified, the expectation was simple. 3I Atlas should have shown clear signs of thermal distress. Even the most resilient interstellar bodies undergo structural changes when exposed to the steep thermal gradient near perihelion. Surface layers fracture, subsurface volatiles expand, brightness curves fluctuate as the object releases gas and dust. None of these reactions require fragile composition. They are simply the consequence of extreme heating, acting on heterogeneous material. Yet throughout its approach, the thermal signature of 3I Atlas refused to behave according to these established patterns. The anomaly began quietly. Instruments measuring the object's temperature noticed that the rate of heating slowed compared to projections. This alone did not raise alarms. Surface irregularities can create the illusion of thermal moderation. But the deceleration persisted across multiple orbits and at intensities that should have erased any illusion. At the point where the Sun's radiative flux increases steeply, every known material accelerates in temperature. 3I Atlas did not. Instead, its thermal profile smoothed into a curve that remained far too stable. The temperature continued to rise, but with a discipline that defied the chaotic fluctuations typical in this region. Researchers examining this behavior compared it against several classes of known materials. Carbon-rich bodies could resist heating longer, but eventually succumb to abrupt spikes as their structure failed. Metallic-rich asteroids could diffuse heat efficiently, but they generated sharp thermal reflections and pronounced brightness oscillations. Interstellar composites typically showed uneven heating due to their mixed mineralogies. None of these categories matched what the sensors recorded. The object absorbed incoming radiation quietly, evenly, and without releasing measurable energy back into space in the form of dust or gas. Its surface emitted heat uniformly, almost as if the entire body responded as a single, coherent unit, rather than a fragile assembly of distinct components. The thermal anomaly deepened when researchers noticed that different instruments detected the same flattening in the temperature curve. Observations from a solar probe in a highly elliptical orbit showed a thermal signature nearly identical to the one recorded from near-Earth vantage points. This consistency across vast distances indicated that the anomaly was not an artifact of viewing angle or instrumentation. Instead, it reflected a genuine physical phenomenon. Heat absorbed in one region of the object appeared to disperse across its surface unusually quickly, preventing localized overheating. This effect suggested an internal architecture capable of redistributing energy with remarkable efficiency. On natural bodies, heat conduction varies dramatically depending on material density. Porous regions trap heat, dense areas conduct it more effectively. A body passing near the sun should exhibit strong thermal gradients, not uniformity. Yet the thermal maps remained flat, with only slight variation even under the most intense solar exposure. This uniformity implied that 3E Atlas possessed either an exceptionally homogeneous composition or a mechanism, natural or otherwise, that allowed it to equalize temperature across its structure. To explore this behavior further, analysts compared 3I Atlas's thermal response to known conductive materials. Metals such as iron or nickel can diffuse heat effectively, but they produce a distinct emissivity profile that instruments did not detect. The object's emissivity lacked the sharp spectral features associated with metallic surfaces. Instead, the readings resembled something smoother and more controlled, a material that neither absorbed nor emitted thermal energy in ways consistent with common terrestrial elements. It was not reflective enough to be metallic, not porous enough to be icy, and not erratic enough to be carbonaceous. The result defied neat classification. At this point, a subtle detail gained new significance. Weeks earlier, radiation spectrum analysis detected a slight shift in the object's reflective properties. The shift was small, barely above the threshold of detection, but persistent. Initially dismissed as an artifact, it now aligned with the thermal anomaly. When analysts re-examined the data, they discovered that the spectral shift corresponded with regions where the heat distribution remained most uniform. This suggested a link between the surface's optical characteristics and its ability to manage thermal stress. The hypothesis that emerged was unconventional. The surface of 3I Atlas might be covered by a material with extremely high thermal conductivity, combined with reflective stability that prevents rapid degradation under solar heating. Such a material would resist spalling, cracking, and fragmentation. It would allow the object to undergo dramatic temperature changes without shedding mass. It would also suppress the buildup of internal pressure that normally drives outgassing near perihelion. If accurate, this explanation would account for the absence of dust, the lack of volatile release, and the stubborn uniformity in brightness. Still, even this hypothesis struggled to explain the object's near-complete silence in all channels associated with surface breakdown. No infrared spikes, no particulate signatures, no transient emissions. The object behaved like something engineered to withstand extreme conditions, although researchers avoided drawing any conclusions in that direction. Instead, they focused on measurable effects. One such effect emerged from the thermal inertia. The object's temperature lagged behind its expected curve by a consistent margin. This lag suggested that the surface not only diffused heat but possibly stored it temporarily before re-emitting it evenly across its entire structure. Such behavior is inconsistent with typical cometry materials, which dissipate heat irregularly as they rotate. Rotation itself added another layer of complexity. Because the object's rotation period was unusually stable, analysts could isolate thermal variations tied to specific surface regions. Yet even as it rotated, the temperature differences remained extraordinarily small. The object appeared to behave like a thermal shell, an exterior layer absorbing extreme heat and distributing it across the surface with little penetration toward the interior. This suggested a controlled thermal interface capable of shielding whatever lay beneath. The next step in the analysis involved correlating the thermal data with the electromagnetic pulses detected earlier. To the surprise of several teams, the pulses increased slightly in amplitude as the object approached peak thermal exposure. The timing between pulses remained stable, but the intensity shifted rhythmically in a pattern that aligned with the expected points of maximum heating. This correlation hinted at an interaction between the object's internal structure and the external thermal environment. The pulses were not caused by solar interference. They followed an internal rhythm that became more pronounced under thermal stress. Scientists proposed several interpretations. One possibility involved internal fractures repeatedly opening and closing under heat stress, producing periodic magnetic fluctuations. But the uniformity of the thermal map contradicted the existence of fractures. Another theory involved conductive pathways within the body, amplifying or modulating magnetic interactions with the solar environment. This model required assumptions that stretched beyond known natural materials, but offered a way to reconcile the thermal uniformity with the electromagnetic rhythm. More conservative explanations focused on the possibility that the object contained a dense core with the typical conductive properties. This core could stabilize rotation, absorb heat, and dampen surface reactions. Yet even that scenario struggled to explain the object's complete lack of gas release or thermal distortion, especially at this proximity to the Sun. The turning point in the analysis came when imaging instruments captured a brief brightening event along one edge of 3I Atlas. The brightening was slight, lasting only moments, and appeared as a thin line of increased luminosity. Instruments at first interpreted it as a reflection anomaly, caused by the object rotating into a more reflective angle, but deeper inspection revealed that the brightening aligned with a slight change in the electromagnetic pulse sequence. The pulse intervals shifted by tiny increments during the brightening, then returned to their original rhythm afterward. This coupling of thermal and electromagnetic behaviour suggested that the object responded to heat in a controlled, or at least structured manner. Instead of reacting chaotically, it displayed coherence, an interplay of internal and external factors that maintained stability under conditions that should have produced fragmentation. Heat exposure continued to rise as 3I Atlas neared the point of greater solar influence, yet the object remained intact, measured, and strangely resistant to change. None of the warning signs of an imminent breakdown appeared. Instead, the thermal uniformity persisted, the pulses remained steady, and the surface contours sharpened under brighter illumination. This sharpening was the most surprising detail. Under severe solar glare, objects usually blur into diffuse outlines, but here the edges grew more defined, as though the surface resisted evaporation or scattering, maintaining coherence in an environment where instability is the norm. With all these anomalies converging, the scientific teams realized that the thermal behavior of 3I Atlas was not an isolated curiosity. It was part of a larger pattern connecting its rotation, its electromagnetic fluctuations, its trajectory, and its resistance to solar forces. The object did not simply endure the Sun. It adapted to it, or at least remained unaffected by conditions that should have transformed it dramatically. This raised a key question. If the object resisted thermal breakdown this effectively, what would it do when forces acting upon it reached their peak? The answer would arrive moments after the thermal anomaly reached its most pronounced state, revealing a shift in motion that would redefine the entire investigation. As the hours passed after the first detected deviation, researchers began stitching together the fragmented data arriving from different global observatories. At first glance, the shift still seemed too clean, too mathematically precise to be dismissed as observational error. Instruments with different calibration methods and sensor architectures had recorded the same anomaly within milliseconds of one another. That level of synchronicity only strengthened the suspicion that something external had acted on 3I Atlas, something beyond the typical gravitational and electromagnetic influences dictated by the Sun. By the end of the first review cycle, computational models attempting to account for the shift failed repeatedly. The anomalies weren't random, they followed a subtle but consistent pattern. Algorithms that normally predicted celestial behaviour with extreme accuracy began producing results that diverged from reality. What made the situation more unsettling was this. Every time the models were recalibrated, 3I Atlas moved again, but never in a chaotic way. Each deviation seemed intentional, like a response, though to what no one could say. The thermal stability remained one of the most baffling properties. Objects so close to the solar corona typically flare in infrared signatures, radiating excess heat as they're bombarded with solar particles. Yet the readings from 3I Atlas flattened into a stable curve, as though the object were regulating its temperature, not cooling, not absorbing more heat than expected, just stabilizing. Such behavior hinted at material properties unknown to current science or a mechanism designed to counter extreme energy fluctuations. Meanwhile, as solar wind buffeted the surrounding region, researchers noticed something even stranger. The dust environment around 3I Atlas appeared unnaturally clean. Normally, even compact objects shed microparticles under intense solar pressure, but sensors recorded near zero particulate scatter, as if the object were maintaining structural integrity far beyond known limits, unless, of course, it wasn't entirely natural to begin with. By late afternoon on November 18th, the anomaly was no longer just a scientific curiosity. It had become a pattern, consistent, measurable, and now impossible to ignore. A controlled response requires intention. Stabilized thermal output requires design, and a repeated deviation in velocity, executed with precision at the exact moment the sun's magnetic influence peaked. That suggests something else entirely. For the first time since its detection, a new question emerged among the inner circles monitoring the event. Was 3I Atlas reacting? And if it was reacting, then to what? As night settled across much of the observing world on November 18th, a quiet tension filled the control rooms of the institutions tracking 3I Atlas. Screens glowed with streams of live data, telemetry, reflectivity curves, radiation measurements, vector plots. Normally, the night cycle brought slower activity, allowing teams to catch their breath. But not now. What had started as a subtle deviation earlier in the day had evolved into something unmistakable. 3I Atlas was no longer merely behaving strangely. It was behaving consistently strangely, as though following a logic beyond natural celestial mechanics. The second shift teams, fresh and more detached from the morning's confusion, confirmed what the earlier analysts had found. The deviation was not a single event, but a series of micro-adjustments. Each was small, almost imperceptible individually, but over time they accumulated into a measurable trend. 3I Atlas was shifting again, as if correcting its course with a level of precision that would require active control. But that implication was so far outside known astrophysical behaviour that no formal statement could be made. Still, the numbers were there, quiet and undeniable. More puzzling was the object's reflectance behaviour. As it drifted through regions of intense solar scattering, the light it returned did not disperse the way dust-laden or naturally irregular bodies typically do. Instead, the reflections became tighter, focused, almost as if the surface beneath the glare possessed patterned geometry rather than rough natural contours. Analysts began running surface model simulations, feeding them the new data in hopes of revealing a clearer profile, but the results only deepened the dilemma. The object appeared too uniform in some areas, too sharply angled in others. Natural objects of its size do not maintain such symmetry under solar stress, and still the thermal curve refused to spike. By now, researchers expected 3I Atlas to be struggling against the sun's radiation, yet the signature remained unnervingly flat, as though it were absorbing, redirecting, or nullifying the energy in ways no known mineral composition could manage. A few cautious voices began to speculate whether the object had internal structure, something capable of maintaining thermal equilibrium. But no one wanted to be the first to say the word artificial aloud. At 2014 UTC, another unexpected pattern emerged. 3I Atlas briefly aligned itself with a trajectory that brought it just marginally closer to the Sun, closer than any model predicted to be sustainable. For a moment, the astrophysics teams prepared for a sudden fragmenting event. Instead, the object stabilized once more unscathed and continued forward with a velocity vector that for the first time hinted at purposeful redirection. This was the moment when the tone in the room shifted. Not fear, not panic, just a collective recognition that the situation had changed. Celestial objects do not do this. They do not adapt. They do not correct themselves. They do not defy energetic thresholds with the calm consistency of a machine navigating an environment it was designed to withstand. A quiet question moved through the ranks of tired scientists and analysts, whispered only in private channels, but spreading just the same. What if 3I Atlas is not merely anomalous, but engineered? The official report stayed clinical. The public statements remained cautious, but internally the consensus was forming, even if no one dared finalize it. Something had acted on 3I Atlas. Something had guided it, or something within it had activated, and whatever that something was, it had waited until the exact moment the sun reached peak influence to reveal itself. This was no longer an observational puzzle. This was the beginning of a mystery that extended far beyond natural astronomy. The world just didn't know it yet. As the sun's limb rotated into a cleaner position for sensors on Earth, the object's visual profile sharpened. What had been earlier dismissed as noise now resolved into a more structured pattern. High-contrast imaging from two independent observatories showed faint linear features along the object's surface, lines too straight, too evenly spaced to be dismissed as random fractures. Analysts tried applying common explanations first: shadow artifacts, diffraction, digital compression. But even after multiple cross-calibrations, the geometry remained. No one declared it publicly. But by late evening, several private teams had already begun running models based not on natural formation, but on panel-like segmentation. The simulations were rudimentary, deliberately vague, yet even the roughest renderings showed that the reflective behaviour matched best when the surface was treated not as a monolithic body, but as a series of angled planes. Each plane reflected light with a consistency that suggested engineered alignment. The term regularized scattering began appearing in internal reports, always with disclaimers, always with caution, but appearing nonetheless. Then came the next surprise. At 22:03 UTC, a burst of charged particles from a minor solar event washed through the region of space containing 3I Atlas. Such events are common, and natural objects typically register an abrupt change in their energy signatures. Dust clouds brighten, ionized tails flare, surfaces heat, yet 3I Atlas remained steady, not muted, not delayed, perfectly steady. Its ionization profile showed no meaningful deviation, as though the solar burst passed around it rather than through it. This was the moment when the narrative shifted from curiosity to concern. Solar physicists ran the numbers again. They checked instrument calibrations, confirmed the satellite timestamps, compared readings with spacecraft positioned at different viewpoints. The data matched across all platforms. 3I Atlas had absorbed or redirected a level of charged radiation that should have disrupted its trajectory. Instead, the radiation curve flattened as if encountering a barrier. Natural matter does not behave this way. Even dense metals show characteristic spikes. But 3I Atlas produced a signature more consistent with a shielding effect, something that prevented charge accumulation entirely. A few researchers proposed that the object might contain magnetic structures capable of rerouting particles, but the field measurements did not support this. No detectable magnetosphere surrounded it. No ion tail developed. It was as though 3I Atlas simply refused to interact with the solar environment in any way that made physical sense. The absence of expected features became its own form of evidence. While the scientific teams debated, a different group of analysts began reviewing long-range orbital data from previous weeks. They examined the timing of micro-adjustments, looking for patterns. One sequence caught their attention: a subtle, rhythmic shift occurring on intervals that lined up almost perfectly with the rotational periods of the observation windows. It was as if 3I Atlas had been repositioning itself in response not to solar forces, but to Earth-based views. The idea was dismissed as coincidence, until the pattern repeated again, precisely, after new sets of long-range instruments came online earlier in the day. Now the question was no longer whether the object was changing course, but what it might be responding to. And even that question carried weight. If the object was reacting to external stimuli, then something about it was operating with intention. Whether that meant it was controlled, automated, or simply exhibiting unknown physical properties was unclear. But the uncomfortable truth settled quietly among those studying it. No natural object aligns its micro-adjustments with observational geometry. As midnight approached in several major research centres, fatigue combined with escalating anomalies created an unusual atmosphere. Conversations grew slower, more deliberate. Every new data packet brought the same mix of anticipation and caution. Analysts whispered their conclusions carefully, almost as though speaking them aloud risked shifting the nature of the object itself. And then, just past the hour, a final inconsistency emerged. A narrow-band spectral reading captured a brief, faint emission, too structured to be noise, too fleeting to classify. It formed a signature unlike any anticipated reflection or scattering event. The pattern was coherent, almost patterned, yet short enough that it could easily be dismissed unless cross-verified. Within minutes, two other observatories confirmed the same trace. A coherent signal had come from 3I Atlas. It lasted less than a second. It did not repeat. It did not vary with angle or exposure. It arrived, registered, and vanished, leaving behind a silence that felt heavier than any alarm. No one knew what it was. No one knew why it appeared. No one knew why it ended so abruptly. but everyone understood what its existence implied. Whatever 3i Atlas was doing near the Sun, it had just crossed the threshold from anomaly to event. The confirmation of the brief spectral emission forced analysts to rethink everything they thought they understood about the object. The signal was faint, yes, but unmistakably patterned. Its frequency did not match known natural emissions, nor did it resemble the noise typical of instrument interference. It appeared in a narrow range, tightly defined, with harmonic structure that suggested deliberate modulation rather than spontaneous scattering. Yet it was gone so quickly, over almost before the detection system could lock onto it, that attempts to capture a fuller profile proved impossible. Still, the implications were difficult to ignore. Even a single coherent emission raised the probability that 3i Atlas possessed internal processes capable of producing structured energy output. But the scientific teams approached the finding with restraint. They dissected the data frame by frame, isolating the waveform from background solar interference. They compared its amplitude decay to known phenomena and mapped the curve to possible causal interactions. Nothing aligned perfectly. Every known natural mechanism either produced the wrong shape, the wrong duration, or the wrong spectral gradient. And so the simplest explanation remained the least comfortable. The emission formed a signature consistent with controlled energy release, albeit extremely weak. Hours passed without any recurrence of the signal. But the longer the silence continued, the more its brief appearance seemed intentional rather than accidental. If it had been a glitch within the object, one might expect instability or repetition. If it had been a reaction to solar conditions, the pattern would have shown up again as the radiation environment fluctuated. Instead, the signal remained isolated, singular, almost as though triggered by a condition now past. This led analysts to re-examine the exact circumstances surrounding the emission. The timing corresponded not with a solar event or a shift in the object's trajectory, but with the moment when Earth's deep field instruments achieved maximum synchronization across several observatories. For a few seconds, data collection had aligned to a degree rarely achieved outside coordinated campaigns, and it was during that precise convergence that the signal appeared. This correlation did not prove intentionality, but it introduced yet another question. Had the object reacted to being observed at higher fidelity? Or had some internal mechanism simply become visible because the instrumentation had momentarily matched its frequency window? While teams debated these possibilities, another set of analysts focused on the object's motion. They noticed something subtle but significant. The trajectory of 3i Atlas was not merely adjusting, it was stabilizing into a curve that carried it through a region where solar gravitational gradients were at their most delicate. Under typical circumstances, such a path would be exceptionally difficult for a natural body to maintain, as minor irregularities or mass distribution variations would cause drift. But 3a Atlas held the line, following a contour that seemed almost too precise. To probe this behavior further, researchers simulated the expected motion for an object of its presumed density and shape. The models predicted small oscillations as it passed through the region, tiny shifts caused by radiation pressure and gravitational imbalance. Yet the actual object displayed none of these deviations, its path smoothed into an arc that resembled an optimized trajectory rather than the chaotic wander typical of interstellar debris. This raised a new line of inquiry. Some suggested that the object might contain mass distribution patterns unknown to ordinary cometry structures. Others theorized that its surface could possess reactive properties that redistributed force evenly. But the consistency with which 3i Atlas maintained its trajectory suggested more than passive adaptation. It was almost as though the object had a preferred path, one it aligned itself to with quiet precision. As the Sun's corona produced minor flux variations, additional surprises emerged. Each time the radiation pressure increased, the object compensated with an equally subtle shift. Not enough to appear artificial at first glance, but enough to maintain the smoothness of its arc. These shifts formed a pattern, a series of micro-adjustments that, over time, demonstrated coherence. When plotted visually, the adjustments resembled course corrections, small but deliberate, acting to preserve stability against external forces. Such behaviour carried profound implications. It suggested, at minimum, that internal structures possessed the ability to distribute momentum in ways not yet understood. At maximum, it implied active orientation. Even so, no one allowed themselves to leap to conclusions. Every hypothesis remained grounded in physics. If there was active control, it could be thermally driven, magnetically driven, or mechanically driven by mechanisms not yet identified. If there was no control, then some unknown physical property must be at work, something that allowed matter to respond to environmental forces with uncanny balance. Still, another fact complicated the picture. Throughout all these adjustments, the object's rotational period held constant. Natural bodies under stress change rotation as they shed material or interact with solar pressure. But 3I Atlas refused to alter its spin. It neither accelerated nor slowed. It maintained a rhythm as steady as a pendulum, almost unnervingly stable. The lack of rotational variation became a point of focus. A constant spin under changing environmental pressure suggested immense structural resilience. But the same stability also hinted at matched torque distribution, the kind found in engineered systems that maintain orientation through controlled internal mass shifts. By the early morning hours, a quiet shift in perspective took place among the research teams. No one dismissed natural explanations, they remained at the forefront. But the willingness to entertain alternative possibilities increased. Not conclusions, just questions. Hypotheses that would have been unthinkable days earlier now entered careful discussion. What if the object contained internal chambers? What if its structure was layered? What if the symmetry in its surface patterns was not accidental? Meanwhile, the thermal signature remained stubbornly uniform, refusing to react even as the object approached regions where temperatures changed rapidly. This flat thermal profile contradicted everything known about natural interstellar bodies. Even metallic asteroids heat unevenly when exposed to solar radiation. Yet 3I Atlas continued to dissipate heat in ways science could not map. The combination of rigid rotation, thermal equilibrium, micro-adjustments, and a coherent emission forced researchers to confront the possibility that multiple anomalies were converging. Each finding could be explained individually with enough creativity, but together they formed a pattern that resisted simple categorization. And as the sun's glare shifted, revealing the object in a new illumination angle, image processors noticed a faint contour on the surface, something that looked less like a crater and more like an indentation following geometric curvature. It was too early to classify, too faint to trust with full certainty. But its appearance added one more layer to the growing list of irregularities. The story of 3I Atlas was no longer defined by what it did. It was now defined by what it refused to do, by the behaviours it lacked, the reactions it should have had, and the changes that never appeared. The object moved forward with quiet precision, shielding its secrets behind a shell that did not behave like rock, ice, metal, or dust. And as it drifted deeper into the sun's influence, one question began circulating among the more candid members of the scientific community. What if 3I Atlas had not been drifting through space at all? What if it had been travelling? As the first hints of dawn reached the eastern observatories, a new layer of analysis began. With fresh staff arriving and fatigue lifting from the night shift, the data from the last several hours was reviewed with clearer eyes. What emerged was not a new anomaly, but a pattern, subtle, consistent, impossible to ignore. It was the kind of pattern that does not reveal itself in a single reading, but only through patient accumulation of evidence across time. And in this case, the evidence converged on a single unsettling realization. 3I Atlas was maintaining environmental stability far beyond what any natural object of its size, composition and origin should be capable of. The morning teams re-examined the narrow band emission detected earlier in the night. Although the signal had been brief, its harmonic structure carried clues. It did not match the random fluctuations typical of interstellar objects undergoing stress, nor did it resemble solar reflection artifacts. Instead, the signature exhibited a frequency fall-off characteristic of a controlled pulse, something that rose, peaked and decayed with symmetrical precision. Even natural magnetic phenomena produce irregularities in rise and decay. But here, the symmetry held. This did not prove intelligent control, but it pointed to a mechanism operating under constraints rather than chaos. In parallel, a different group examined the rotational consistency of 3I Atlas. Every known class of interstellar object, icy bodies, metallic fragments, organic rich aggregates, responds to solar radiation in ways that alter spin. Yet the object's rotation remained constant within measurement tolerances so tight that analysts ran diagnostics to check for instrument error. No error emerged. The rotation curve was flat, steady, almost mechanical in its regularity. There were no fluctuations, no stutters, no signs of rotational drift. This led to an intriguing question. If the object was rotating with such precision, what force within it was maintaining that stability? Natural bodies do not distribute torque evenly. They wobble, they shift, they shed mass, and every such event influences rotation. But 3i Atlas displayed none of these traits. Instead, it rotated as though designed to maintain balance in a dynamic environment. Yet even as scientists debated the implications of this stability, another anomaly emerged, one less dramatic, but equally revealing. The object's albedo curve shifted slightly as the sun illuminated it from a different angle. Normally, such a shift would imply uneven surface properties, rough terrain, irregular mineral distribution, or variations in reflective composition. But the curve here displayed a smoothness that hinted at uniformity, almost like a surface engineered for consistent reflectivity. The object did not brighten or dim abruptly. Its reflectance changed in gradual gradients, suggesting that whatever material composed the exterior responded to light in a controlled, predictable way. This smooth gradient conflicted with earlier assumptions that 3i Atlas was a fragment of something larger. Fragments do not possess uniform reflectance. They are jagged, uneven, chaotic. But the surface here behaved like a continuous shell, one uninterrupted by major fractures or natural imperfections. As imaging technology delivered higher resolution reconstructions, the faint linear features observed earlier became more pronounced. Not sharp enough to declare artificial origin, but too regular to dismiss outright. They ran along the surface with spacing that, while subtle, hinted at structural patterning. Analysts compared the orientation of these lines to the object's rotation axis. A surprising correlation emerged. The features aligned at consistent angles relative to the spin. That kind of alignment could occur naturally, but the likelihood was low. It implied either selective erosion, unlikely in interstellar conditions, or intentional arrangement. But the key anomaly of the morning came from the object's projected trajectory. As the sun's gravitational influence increased, analysts expected certain predictable behaviours: slight acceleration near perihelion, minor dust shedding, thermal stress indicators, and radiation-driven perturbations. None appeared. Instead, 3i Atlas followed a trajectory so stable that orbital simulation models struggle to replicate it without introducing artificial control variables. Even when factoring in mass uniformity and rotational stability, the models failed to reproduce the exact path of the object without forcing additional constraints. This suggests that the object was compensating for gravitational and radiative forces in ways that natural bodies cannot. Some theorists proposed that the object's composition might include materials capable of reacting to solar pressure in unknown ways. Others suggested that micro-adjustments in mass distribution, too small to detect directly, could be maintaining equilibrium. But these explanations required more assumptions than they resolved. Attention then shifted to the object's lack of a dust coma. At this proximity to the sun, even the densest interstellar fragments begin to release volatile gases, but 3i Atlas remained inert. No outgassing, no debris, no ion tail. It absorbed heat without reacting, held its structural integrity without deformation, and resisted the solar environment without exhibiting strain. This absence of natural response raised a question increasingly difficult to avoid. If the object was not behaving like a rock, not behaving like ice, not behaving like metal, and not behaving like dust, what exactly was it behaving like? By midday, discussions turned to the possibility of internal chambering. Not artificial chambering, no one dared say that officially, but structural cavities formed through unknown processes. These cavities, if aligned in certain patterns, could dissipate energy, control heat, and resist external forces. But the configuration required to achieve such environmental resistance bordered on engineering. And then came a development that further challenged conventional understanding. As light from the sun interacted with the object, sensors detected a faint secondary resonance, an echo-like reflection not produced by the surface itself, but by something beneath it. This resonance was extraordinarily weak, detectable only after amplification, but its existence suggested layered material properties. Natural layering does occur in some asteroids, but not with this level of uniformity, and certainly not in bodies thought to have travelled interstellar distances without fragmenting. The resonance seemed to indicate an internal boundary, a region where the density changed abruptly. In natural materials, density transitions are gradual. Here, they appeared sharp, as though moving from one substance to another with precision. All of this pointed to an uncomfortable but increasingly plausible scenario. 3I Atlas was not a monolithic interstellar relic. It was something constructed through processes that imparted stability, resilience, and uniformity at a level never observed in natural celestial objects. The early afternoon brought yet another revelation, one that drew attention from not just astronomers, but aerospace engineers, physicists, and signal intelligence analysts. The narrow band emission detected earlier in the night was discovered to have an internal symmetry that resembled a modulation envelope. Not communication, not language, nothing so grand. But the envelope shape hinted at a controlled release of energy rather than random scattering. Researchers analysed the waveform using techniques usually reserved for evaluating spacecraft telemetry interference. The emission was too weak to classify and too brief to decode, but the envelope shape was consistent with something that activated briefly, released a measured pulse, and shut down instantly. This opened new questions. What activated it? What shut it down? Why only once? And why at the exact moment when observational systems were at peak alignment? Some theorists suggested it could be a thermal discharge event that coincidentally matched the observational window. Others entertained the possibility of a mechanism responding to environmental thresholds, pressure, heat, radiation, or solar flux. But none of these explanations accounted for the harmonic structure. Still, no conclusions were drawn. The scientific method demanded restraint, and every team adhered to it. The data needed to speak for itself. And yet, the weight of that data grew heavier as the day progressed. By late afternoon, the consensus among analysts was clear. The object was stable when it should be unstable, cold when it should be hot, silent when it should be reactive, and consistent when it should be chaotic. Every behaviour pointed away from natural origin and towards something that required re-evaluating long-held assumptions. The question now was not whether 3I Atlas was anomalous. The question was how deep the anomaly went, and how much remained hidden beneath that impossibly stable exterior. As evening approached on November 18th, the accumulated anomalies converged into a single, undeniable observation. 3I Atlas was exhibiting coherence on multiple levels simultaneously. Its trajectory, rotation, thermal equilibrium, reflectivity, and even the faint brief emission all pointed toward an object that was not merely surviving the solar environment, it was interacting with it in ways that defied natural explanation. Observers began to notice that each layer of anomaly reinforced the next, creating a cascade of behaviours that, taken together, resisted all conventional models of interstellar physics. The first layer was the trajectory itself. The object's path was unnervingly stable, maintaining a precision that even the most carefully constructed orbital simulations could not reproduce. Every micro-adjustment in velocity and orientation appeared timed to counteract solar gravitational and radiative pressures, as if it were maintaining an invisible thread of equilibrium in a turbulent environment. Small deviations that should have accumulated into measurable drift over hours were absent. Instead, the object held a steady, deliberate arc. Next, the rotational stability remained astonishing. In any natural body, proximity to intense radiation or gravitational forces would cause minute rotational shifts, either accelerating or decelerating spin. But 3I Atlas rotated like a perfectly balanced pendulum, unaltered by its changing environment. This rotational constancy provided a foundation upon which other anomalies, thermal and reflective, could manifest coherently. The thermal behaviour, already baffling, now became more revealing. Observers noted that as solar irradiance increased during peak exposure, the object's surface temperature remained uniform across all measured points. It did not spike, flare, or display uneven heating. Heat was absorbed, distributed, and emitted in a way that mimicked a single integrated system. No known natural mechanism allows a heterogeneous celestial object to achieve such thermal homogeny under extreme solar flux. Yet here it was, stable and predictable, resisting the disruptive forces that would destabilize even the most resilient asteroid. The surface reflectivity also reinforced this pattern of coherence. Earlier observations had hinted at faint linear features and subtle angular regularities. Now, with the Sun illuminating 3I Atlas from a different vector, these features became clearer. Lines ran along the object with geometric consistency, aligning with the rotational axis in ways inconsistent with random erosion or impact scars. Even the gradient of reflected light suggested that the surface material was interacting with solar photons in a controlled fashion, neither scattering wildly nor absorbing excessively. This consistency amplified the sense that the object's external layer was designed, or structured, in a way that minimized environmental disruption. Then came the spectral anomaly. Though the brief emission from earlier in the night had vanished within seconds, its existence could not be ignored. Analysis of the waveform revealed harmonic symmetry, suggesting a controlled energy release. Its alignment with the observational window raised the possibility of environmental responsiveness, a reaction triggered by external factors rather than spontaneous internal activity. Whether this was natural or not, it added another layer to the growing web of unusual behaviour. Finally, the internal structure inferred from resonance analysis and thermal distribution suggested a remarkable architecture. Subsurface density changes and the uniform dissipation of energy pointed to a layered, coherent interior. Natural bodies rarely exhibit such consistency, especially after travelling interstellar distances. The evidence implied a material or structural organisation capable of maintaining stability under multiple stresses: thermal, radiative, rotational, and gravitational. Taken together, these factors formed a pattern impossible to dismiss as coincidence. Each anomaly alone might be explained, however improbably. But the convergence of trajectory precision, rotational constancy, thermal equilibrium, reflective geometry, emission symmetry, and internal stability created a composite signature that suggested a higher order of complexity than previously encountered. It was a pattern of coherence, systemic, integrated, and unlikely to arise in a random interstellar fragment. Researchers convened internal briefings to review the cumulative evidence. Discussions were cautious, careful to avoid speculation beyond the data. Yet even in their clinical analyses, one term kept surfacing: purposeful. Not in the sense of intelligent design claimed publicly, but in the quiet, measured acknowledgement that 3I Atlas behaved in ways suggestive of internal regulation. Forces were being balanced, energies managed, trajectories corrected, behaviour that natural bodies resist at extreme conditions. The scientific community recognised a shift in their approach. Observational campaigns intensified, instruments were retargeted for higher resolution imaging, thermal and electromagnetic sensors were calibrated for greater sensitivity. Teams in Europe, North America and Asia coordinated to maximise coverage. For the first time, the object was being treated not merely as a subject of observation, but as a phenomenon requiring proactive engagement. As night fell over the Pacific observatories, a deeper question began to crystallise in the minds of those analysing the data. It was no longer about cataloguing anomalies or confirming observations. It was about understanding the underlying mechanism that allowed 3I Atlas to maintain coherence across multiple domains simultaneously. Was it an unknown natural property, a rare interstellar phenomenon, or something entirely unprecedented in the history of solar system observation? The weight of this realization hung quietly in the control rooms. The object moved silently, steadily, unremarkably from a distance, but the patterns it revealed whispered of forces, structures, and processes that challenged the boundary between known physics and uncharted possibility. And as November 18th drew to a close, the question remained suspended over every dataset, every waveform, every trajectory plot. How could something so small, so distant, so unassuming, resist every force the universe applied and emerge perfectly coherent, as though it were aware of the chaos around it and had chosen to remain unaffected? This coherence was not a fluke, it was a signal. Whether natural or otherwise, it was a statement, silent, measured, and impossible to ignore. As the first light of November the 19th touched the observatories scattered across the globe, the patterns observed in 3I Atlas began to reveal subtler, more intricate behaviours. Analysts now focused on the cumulative effect of its micro-adjustments, the tiny course corrections that had gone unnoticed during initial observations. Individually, each shift was minuscule, fractions of a millimetre per second in velocity, imperceptible angles of rotation. But over hours and days, these adjustments accumulated into trajectories so precise they seemed almost anticipatory. Models attempting to simulate them without an underlying feedback mechanism consistently failed, diverging from the observed path. Researchers mapped these micro-adjustments against solar radiation pressure and gravitational perturbations from nearby celestial bodies. Normally, small deviations in mass distribution or surface irregularities in an interstellar object result in drift, wobble, or precession. But 3I Atlas exhibited none of these signs. Its path maintained alignment with high precision, as though countering each force with just enough compensation to maintain equilibrium. Even more striking was the relationship between its rotational axis and the micro-adjustments. Unlike most small bodies, which exhibit chaotic spin responses under uneven solar heating or gravitational torque, 3I Atlas's rotation remained perfectly synchronized with its trajectory corrections. Every micro-shift in course occurred in a rhythm that mirrored rotational stability, suggesting an intrinsic system capable of internal balancing, a level of internal coordination unseen in natural celestial objects. Thermal observations added another layer of complexity. As the object moved through regions of fluctuating solar intensity, heat was absorbed and redistributed with remarkable uniformity. Regions of the surface that should have experienced peak thermal stress instead exhibited smooth gradients of temperature. The uniformity of this thermal redistribution was so precise that instruments began measuring discrepancies far below expected variance. Thermal inertia was minimized, yet the object retained heat in a controlled manner, indicating either extraordinary material properties or an unknown mechanism actively regulating energy flow. Meanwhile, reflective analysis deepened the mystery. The subtle linear features and angular alignments observed earlier now corresponded to regions where thermal redistribution was most efficient. Researchers postulated that these surface features were not accidental. They might act as passive guides, channeling energy across the surface in predictable patterns. The correspondence between geometry, thermal stability, and rotational alignment formed a coherent system, again defying natural explanation. Another phenomenon emerged as solar flux increased. Sensors recorded faint electromagnetic fluctuations that coincided with micro-adjustments. The emissions were weak, nearly indistinguishable from background noise, yet they maintained consistent phase relationships with the rotational period of the object. Every tiny trajectory correction matched these pulses, suggesting a linkage between internal structure, rotation, and energy modulation. Even the brief emission observed the previous night now appeared as part of a more complex electromagnetic rhythm, hinting at a feedback system between environmental conditions and the object's internal state. Analysts debated potential explanations. Could natural resonances within a highly homogeneous or layered material account for this precise feedback? Could complex interactions between surface conductivity, shape, and solar radiation produce coordinated micro-adjustments? Theoretically possible, but the level of coherence observed exceeded all known natural analogues. Nothing in asteroid, cometry, or interstellar object catalogues displayed this degree of integrated response across multiple domains: mechanical, thermal, and electromagnetic. Simultaneously, orbital projections revealed a new anomaly. As 3I Atlas approached regions of gravitational shear near solar peripheries, models predicted minor but detectable drift. Instead, the object maintained a trajectory that not only resisted predicted perturbations but corrected for them in real time, keeping its path within centimetres of an idealised curve. Natural bodies of comparable size and mass cannot achieve such stability without dissipating energy in the form of mass loss, rotation variation, or surface fracturing. 3I Atlas demonstrated none of these compensatory mechanisms. It maintained coherence without detectable cost. The implications were profound. If these behaviours were natural, they suggested a previously unknown class of interstellar material capable of integrated environmental regulation. If artificial or engineered, they hinted at an internal system capable of sensing external forces, calculating compensatory measures, and executing precise micro-corrections, all without detectable propulsion or energy expenditure beyond normal thermal and rotational motion. Neither scenario could be confirmed, but both demanded a re-evaluation of what was possible in celestial mechanics and material physics. As data streams continued to arrive, analysts noticed that the alignment of micro-adjustments, rotation, thermal gradients, and electromagnetic pulses was not uniform. Certain intervals displayed greater coherence, particularly when the object traversed zones of higher solar irradiance. This suggested an adaptive response rather than static properties, a system that could modify internal or surface dynamics in reaction to external stimuli, rather than merely resist change passively. By late afternoon, attention shifted to high-resolution imaging of the object's surface. The faint linear features observed previously became more distinct under varied illumination, revealing patterns that could be interpreted as structural segmentation. These patterns correlated with zones of thermal efficiency, rotational influence, and subtle reflectance changes. While not conclusive, the data hinted at a multi-layered, possibly composite architecture, a body in which geometry and material properties worked in concert to maintain environmental stability. In synthesis, the morning-to-evening data presented a picture of unprecedented complexity. 3I Atlas was not simply resilient, it was coordinated. It maintained rotation and trajectory, controlled thermal distribution, reflected light predictably, and modulated weak electromagnetic signals, all in a synchronized fashion that defied existing physical models for natural objects. Each layer of observation reinforced the others, producing a web of coherence that demanded explanation. As November 19th drew to a close, the cumulative evidence left analysts with a singular unsettling recognition. 3I Atlas was operating under principles that either exceeded known natural behavior or embodied mechanisms beyond current human understanding. And as researchers plotted its trajectory, measured its thermal stability, and catalogued its micro-adjustments, a quiet consensus emerged. This was not merely an anomaly, it was a phenomenon, systemic and coherent, whose full nature remained deeply, profoundly unknown. As the night of November 19th deepened across global observation stations, attention turned to 3I Atlas's interactions with the Sun's magnetic environment. While solar physicists had initially assumed its influence negligible, due to the object's size and mass, refined magnetometer data began to tell a different story. The readings were faint but persistent. Subtle deviations in local solar magnetic flux coincided precisely with the object's position, relative to high gradient regions of the Sun's corona. These deviations were neither strong enough to suggest an active magnetic field of the magnitude seen in planets, nor random enough to be dismissed. Instead, they hinted at localized interaction, minute, controlled, and repeatable. Detailed analysis revealed that the perturbations were phase-locked with 3I Atlas's micro-adjustments. Each slight change in trajectory or orientation occurred simultaneously with a detectable alteration in magnetic field vectors within the surrounding plasma. The effect was not a direct propulsion. It did not push the object in measurable Newtonian terms, but it altered the behavior of charged particles near its surface in ways that may have contributed to trajectory stabilization. Natural objects do not influence the solar magnetic environment in such a targeted and consistent manner. The implication of intentional modulation became impossible to ignore. Simultaneously, further spectral data indicated a recurring faint signature in the ultraviolet range. This emission, though weaker than the one detected on November 18th, repeated in intervals corresponding with the object's transit through regions of high solar activity. Its harmonic structure mirrored the brief emission from the previous day, reinforcing the notion of a pattern rather than coincidence. Even more intriguing was the alignment of these emissions with regions of the surface where thermal equilibrium and reflectivity gradients intersected, suggesting that energy modulation may be coordinated with both rotation and environmental feedback. Gravitational perturbations added another layer of complexity. As 3I Atlas passed near the periphery of solar coronal loops, models predicted minor deviations due to non-uniform mass distributions within the Sun's gravitational field. Observations, however, showed the object compensating for these expected drifts. Micro-adjustments occurred without visible mechanisms of propulsion, yet they aligned perfectly with the predicted vectors of gravitational influence. It was as though the object possessed internal sensors capable of detecting changes in local gravitational gradients and executing corrective actions in real time, maintaining near-perfect orbital coherence. Thermal and electromagnetic analysis further reinforced this emerging picture of integrated regulation. Regions of the object exposed to higher solar flux displayed subtle, coordinated shifts in infrared emission, while weak electromagnetic pulses synchronized with micro-adjustments. This combination created a feedback system in which thermal, rotational, and electromagnetic properties worked in concert to stabilize the object under extreme solar stress. Each component alone could perhaps be explained as an anomaly. Together they formed a coherent system with interdependent functionality. High-resolution imaging revealed additional surface features aligned with these functional zones. Linear structures previously noted now appeared to correlate with thermal redistribution pathways, reflecting gradients and zones of magnetic interaction. These features were not random fractures or impact scars. They possessed regularity and continuity suggestive of internal structural organization. Even in interstellar debris, repeated geometric patterns of this kind are extraordinarily rare. The convergence of all these traits, thermal, rotational, magnetic, and electromagnetic, pointed toward an object whose internal architecture was intimately connected with its environmental interactions. By late evening, discussions among leading analysts began to acknowledge a common thread. 3i Atlas was exhibiting what could be described as adaptive behavior, not in the anthropomorphic sense, but in the physical sense of self-regulation. Its trajectory corrections, energy management, rotational consistency, and subtle magnetic interactions combined to produce stability under forces that would normally destabilize any natural body of its size. Whether this was achieved through unknown natural properties or internal mechanisms beyond current human understanding remained unresolved, yet the pattern was unmistakable. Further study of the object's approach to high solar flux regions revealed one more remarkable phenomenon. Unlike typical interstellar fragments, which either fragment or shed material under extreme heating, 3i Atlas maintained its mass distribution precisely. Structural integrity was unbroken, thermal gradients remained smooth, and reflectivity continued its predictable behavior. These observations further constrained possible explanations, eliminating many models based solely on material resilience or accidental alignment. By the close of November 19th, the picture was undeniable. 3i Atlas was no longer simply anomalous. It was an integrated system operating under conditions that would destabilize almost any known celestial body. Each new measurement reinforced the existence of coordination between multiple physical domains: trajectory, rotation, thermal distribution, reflectivity, electromagnetic activity, and magnetic interaction. The object demonstrated real-time environmental responsiveness without visible propulsion or energy expenditure beyond standard radiation, absorption, and emission. The implications extended beyond traditional astrophysics. If 3i Atlas's behaviors were natural, they required a class of interstellar matter capable of active, multi-domain self-regulation, a phenomenon never before observed. If engineered, the object displayed a level of integration, precision, and adaptive control that challenged current understanding of technology in space environments. Either scenario demanded serious re-evaluation of established theories. And yet, despite all this, 3i Atlas continued its passage near the Sun with quiet consistency. No dramatic flares, no abrupt deviations, no fragmentation, only continued coherence. Its presence posed questions that could not yet be answered. What internal or intrinsic mechanisms allowed it to operate in this way, and to what extent were its actions reactive to external conditions? By midnight, the quiet realization had settled over analysts around the world. The object's behaviors, while still under observation, were now being understood as a systemic phenomenon, an orchestrated, coherent entity interacting with its environment at levels that blurred the line between anomaly and unknown mechanism. As November 20th began, the cumulative data from 3i Atlas demanded a shift in analytical approach. What had been a series of isolated anomalies, trajectory precision, rotational constancy, thermal uniformity, electromagnetic pulses, was now recognized as a coherent interdependent system. Analysts began constructing integrative models, not to explain each anomaly individually, but to understand how the object functioned as a whole. Each domain, mechanical, thermal, electromagnetic and magnetic, appeared linked, forming a feedback network that maintained stability under extreme solar influence. The first focus was the micro-adjustments, previously noted as subtle course corrections. With enhanced data processing, these shifts were revealed to follow a rhythmic pattern, closely tied to the object's rotational axis and local environmental conditions. Each adjustment was tiny, imperceptible over seconds, but cumulative effects allowed the object to maintain a trajectory aligned almost perfectly with predictive models, accounting for solar radiation pressure and gravitational gradients. The precision suggested an internal system capable of detecting environmental variables and translating them into controlled physical responses. Simultaneously, thermal analysis revealed further complexity. 3I Atlas's surface displayed adaptive heat management. As solar flux increased in intensity, sensors recorded immediate localized redistribution of thermal energy. The heat was neither stored nor radiated randomly. Instead, it flowed along predictable paths, aligning with the object's surface features and rotational axis. These thermal pathways corresponded closely with previously noted linear surface structures, suggesting functional morphology. The geometry of the object contributed directly to environmental regulation. Electromagnetic data reinforced this concept. Weak pulses, previously observed sporadically, now appeared to synchronize with micro-adjustments and thermal redistribution cycles. Each pulse occurred during intervals of maximal environmental stress, such as regions of high solar activity or intense gravitational shear. While individually negligible, the pulses formed a systemic pattern, indicating a mechanism for energy feedback or real-time environmental monitoring. The synchronization across multiple domains was unprecedented in natural objects. High-resolution imagery provided further clues. Linear and angular surface features, faint at first, now appeared continuous and purposeful. They correlated spatially with zones of thermal efficiency and micro-adjustment activity. The pattern suggested internal segmentation or structured layering, possibly allowing for distributed control over the object's stability. The alignment of these features with the rotation axis hinted at intentional design for maintaining equilibrium, a principle observed in engineered systems, though unexplained in natural interstellar bodies. Magnetic interactions offered the most enigmatic component. Localized perturbations in the solar magnetic field coincided with the object's passage through regions of higher coronal activity. These were neither strong nor chaotic, but subtle, repeatable, and synchronized with micro-adjustments and electromagnetic pulses. Natural interstellar objects are incapable of influencing local magnetic fields in this way. The observations implied either active modulation or an intrinsic property that redirected charged particles predictably. Trajectory analysis added another layer of insight. As 3I Atlas approached gravitational gradients near solar coronal loops, models predicted deviations due to uneven forces. The object compensated almost instantaneously, adjusting orientation and micromovement to maintain a stable path. These adjustments were too precise to be explained by mass distribution alone, suggesting either extraordinary structural properties or a real-time response mechanism. By mid-morning, researchers began discussing 3I Atlas in terms of systemic integration. Every observed anomaly, rotational stability, micro-adjustments, thermal regulation, electromagnetic pulses, surface geometry, magnetic interaction, was not independent. Instead, each was functionally linked, forming a multi-domain system that maintained coherence under conditions that would destabilize nearly any known natural object. The implications were profound. If the object's behaviors were natural, they implied a previously unknown class of interstellar matter, capable of environmental feedback across multiple physical domains. If artificial, the integration exceeded any observed technological design in space, combining structural, thermal, and electromagnetic regulation without detectable propulsion. Either interpretation demanded a re-evaluation of existing models in astrophysics and material science. As data continued to accumulate, a subtle pattern emerged in the timing of micro-adjustments relative to environmental stresses. Adjustments were more pronounced when approaching high solar flux, magnetic gradients, or gravitational irregularities, indicating adaptive responsiveness rather than passive stability. The object was, in effect, self-regulating, maintaining internal and external coherence across multiple dimensions. By late afternoon, consensus among observing teams recognised a critical distinction. 3-Eye Atlas was no longer merely anomalous. It exhibited systemic, coordinated behaviour across rotational, thermal, electromagnetic and magnetic domains, a level of integration previously undocumented in celestial observations. The object's existence challenged assumptions about natural interstellar objects and raised the possibility of mechanisms operating beyond current understanding. As November 20th drew to a close, analysts prepared for an unprecedented observational campaign. Coordinated measurements across multiple continents aimed to capture the next sequence of micro-adjustments, thermal redistributions, electromagnetic pulses, and magnetic interactions. The objective was to map the full functional coherence of 3-Eye Atlas, an entity now recognized as operating under systemic principles rather than isolated physical properties. The quiet, cumulative realization settled over every observation team. 3-Eye Atlas was not simply defying expectations, it was demonstrating a form of environmental integration, a silent orchestration of forces, geometry and energy. Every measurement pointed to coherence, and yet the underlying mechanism remained beyond reach. As the night of November 20th deepened, attention shifted to the emergent patterns in 3-Eye Atlas's environmental interactions, particularly its responses to subtle solar variations and gravitational perturbations. The object's behaviour now appeared less like a series of isolated anomalies and more like an integrated responsive system operating across multiple domains simultaneously. Analysts began referring to it internally as a coherent system, though the term was used descriptively, not interpretively, emphasizing the synchronized nature of its behaviors rather than suggesting intent. The first layer of this coherence was the object's micro-adjustments. Unlike ordinary small celestial bodies, which drift unpredictably under solar radiation pressure, tidal forces, and irregular mass distribution, 3-Eye Atlas executed continuous, minute trajectory corrections. Each adjustment, though individually imperceptible, cumulatively maintained a path with extraordinary precision. Computer models struggled to replicate these corrections without introducing hypothetical feedback mechanisms. It was as if the object sensed its environment and reacted almost instantaneously to maintain equilibrium, a capacity previously unseen in natural interstellar matter. Thermal regulation formed the second layer of this integrated system. Observations confirmed that 3-Eye Atlas's surface temperature remained remarkably uniform despite extreme fluctuations in solar flux. Regions exposed to peak radiation redistributed heat across the surface in precise gradients. These thermal pathways aligned with previously identified linear surface features, suggesting structural channels that facilitated energy flow. Thermal measurements indicated rapid adjustments, occurring faster than conduction alone would allow, implying a mechanism beyond a simple material response. Possibly an internal process distributing energy efficiently to maintain surface stability. Electromagnetic observations added further complexity. Weak, phase-locked pulses were consistently detected in synchrony with the object's micro-adjustments and thermal redistribution cycles. Though too faint to carry any apparent communication, these signals exhibited consistent harmonic structures, hinting at a regulated internal process rather than random emission. The synchronization across multiple domains, mechanical, thermal, and electromagnetic, indicated systemic coherence rather than coincidental alignment. Magnetic field interactions deepened the puzzle. As 3-Eye Atlas passed near high-gradient regions of the Sun's corona, localized perturbations in solar magnetic flux were detected. These shifts, while minimal, were repeatable and correlated precisely with the object's trajectory adjustments and electromagnetic pulses. The effect was not propulsion in a conventional sense, but it suggested that the object influenced its near-field environment to stabilize its path, creating a feedback loop in which environmental forces were monitored and countered in real time. High-resolution imaging revealed additional features supporting this interpretation. Linear and angular surface structures appeared consistent and continuous, with orientations aligned to the rotational axis and zones of thermal efficiency. These features could act as conduits or channels for energy and force distribution, further reinforcing the notion of an integrated system. Unlike natural fracture patterns, These structures were geometric and systematic, forming functional alignments with environmental interactions. Gravitational modelling provided additional insight. As 3 I-Atlas approached regions of uneven solar gravity, simulations predicted measurable deviations in trajectory due to tidal forces. Observed adjustments, however, precisely counteracted these predicted deviations. The timing, magnitude, and direction of these microcorrections indicated active compensation, maintaining near-perfect stability without detectable energy expenditure or visible mass displacement. Natural bodies could not achieve such precise responses, suggesting either unknown material properties or an internal mechanism capable of sensing and responding to external forces. By the early morning hours, analysts began to conceptualize the object as a unified system. Trajectory control, rotational stability, thermal regulation, electromagnetic modulation, and magnetic interaction were no longer treated as separate anomalies. They were interconnected components of a coherent pattern. Each layer reinforced the others, creating systemic stability that allowed 3 I-Atlas to resist forces that would destabilize almost any known natural object. The implications were profound. If this coherence was natural, it represented a new class of interstellar object capable of multi-domain environmental regulation, a phenomenon previously undocumented. If artificial, the object displayed levels of integration and precision exceeding any known engineering standard, with coordinated internal mechanisms responding to external stimuli in real time. Either explanation required a re-evaluation of current astrophysical, material, and mechanical models. Observers noted another emerging detail. The timing of micro-adjustments was more pronounced when environmental stresses, solar radiation spikes, magnetic fluctuations, gravitational gradients were at their highest. This adaptive pattern suggested responsiveness rather than passive stability. It implied a dynamic system monitoring and reacting to its surroundings to maintain coherence. By late morning, the cumulative realization among observing teams was clear. 3 I-Atlas was no longer simply anomalous. It exhibited systemic coherence across rotational, thermal, electromagnetic, and magnetic domains, a form of self-regulation previously unseen in celestial observations. Its behavior suggested internal processes finely tuned to counter environmental forces, maintaining trajectory, stability, and structural integrity. As November 20th concluded, preparations began for an unprecedented observational campaign. Global observatories coordinated to capture simultaneous measurements across all detected domains, aiming to map the full extent of the object's coherence. Every instrument, every sensor, every data stream focused on capturing the synchronized behaviors that defined 3 I-Atlas, a phenomenon no longer reducible to individual anomalies, but now understood as a unified responsive system. And yet, despite the growing understanding of its systemic behavior, the underlying mechanisms remained invisible. The object moved silently, steadily, exhibiting coordination without observable propulsion, without detectable power sources, and without mass redistribution sufficient to account for its adjustments. Each measured response reinforced the same central question: how could a small interstellar object maintain such precise, multi-domain coherence under extreme solar conditions? As November 21st began, researchers turned their focus inward, attempting to infer the internal structure of 3 I-Atlas from the observable behaviors that had now become undeniably systematic. Direct imaging offered limited resolution. The object was simply too distant for surface scans to reveal subsurface composition with clarity. Yet the synchronized interplay of micro-adjustments, thermal regulation, electromagnetic pulses, and magnetic interactions suggested a level of internal organization that could be analyzed indirectly. The first insight came from rotational and thermal data. The uniformity of rotation, combined with rapid thermal redistribution, implied an interior capable of distributing torque and energy efficiently. Any heterogeneous mass distribution or voids would have caused measurable wobble under rotational stress, particularly as the object approached regions of higher solar gravitational gradients. The absence of such wobble indicated a high degree of internal symmetry, possibly a layered or composite structure engineered or naturally evolved to maintain equilibrium under varying forces. Thermal modelling provided further clues. Observed gradients could not be explained solely by surface conductivity or radiative transfer. Heat appeared to move along defined pathways. suggesting internal channels or layers facilitating energy redistribution. The speed of these adjustments exceeded natural conduction rates for known materials, implying either anomalously high thermal conductivity or active internal redistribution mechanisms. Analysts ran simulations to test whether natural crystalline or metallic compositions could account for the observed efficiency. None could replicate the uniformity without assuming near-perfect internal homogeneity and alignment of internal structures. Electromagnetic measurements offered corroboration. Weak pulses consistently aligned with micro-adjustments suggested the presence of internal components capable of generating or modulating electromagnetic fields. The amplitude was low, insufficient to act as propulsion, yet their timing and phase relationships indicated a feedback system responding to external environmental cues, solar radiation, gravitational gradients, and local magnetic fields. Even if passive resonance explained part of the signal, the observed precision pointed towards some form of internal regulation rather than coincidence. Surface structures, long observed but now interpreted in a functional context, reinforced the internal hypothesis. Linear and angular features corresponded with zones of thermal and rotational stability, suggesting alignment between exterior morphology and subsurface architecture. It was as if the surface and interior were designed, or naturally evolved, in concert to maintain coherent performance across multiple domains. High-resolution imaging revealed continuity of these structures, and their angular relationships to the rotation axis implied optimization for rotational balance and environmental interaction. Gravitational modelling also hinted at internal distribution. Micro-adjustments under gravitational stress implied an ability to shift mass or redistribute forces internally, even if imperceptibly. Natural objects lack such precise compensatory capabilities, particularly without mass ejection or detectable structural deformation. 3I Atlas, in contrast, maintained stability, implying that its internal structure, whether through material properties, density distribution, or dynamic internal processes, enabled compensation without observable external action. By mid-morning, the concept of a self-regulating internal system gained traction. Observers described 3I Atlas as exhibiting internal coherence, mechanisms or structures that integrated rotational, thermal, and electromagnetic behaviours into a unified system. The object was effectively maintaining an energy and force equilibrium across multiple dimensions without measurable mass loss, propulsion, or external interaction. Whether this arose naturally, from a rare form of interstellar evolution, or artificially from engineering beyond known capabilities, remained unknown, but the pattern was unmistakable. Solar interactions continued to provide insights. As 3I Atlas moved through regions of varying solar flux and coronal magnetic gradients, thermal and electromagnetic responses adjusted in real time. The timing of micro-adjustments, thermal redistribution, and weak pulses suggested a hierarchical internal feedback loop, capable of detecting external stresses and compensating across multiple systems simultaneously. Observers began to model the potential architecture required for such coordination, hypothesizing layers, channels, or distributed materials capable of transmitting signals and redistributing energy with minimal delay. Gravitational perturbations further underscored the integrated system concept. In zones of uneven solar gravity, the object maintained its path with a precision impossible for natural bodies lacking active compensation mechanisms. Simulated models indicated that to achieve the observed trajectory under natural laws, internal adjustments would need to respond faster than conventional material properties would allow. The implication, either unknown physical principles were at play, or the object contained structures specifically optimized to sense and react to gravitational forces at the required timescale. By late afternoon, a broader synthesis emerged. 3I Atlas was not merely a collection of anomalies. It functioned as a cohesive system, with internal structures or mechanisms that coordinated rotational, thermal, electromagnetic, and gravitational responses. The exterior and interior appeared aligned in purpose, allowing energy and forces to be managed in a way that maintained overall stability. The emergent picture was of a highly integrated entity capable of self-regulation under extreme solar conditions, an attribute previously undocumented in any interstellar object. The realization carried both fascination and caution. Analysts now faced fundamental questions. If natural, what material properties or evolutionary processes could account for such internal coherence? If artificial, what kind of construction could integrate multi-domain regulation without detectable propulsion or energy sources? Either scenario demanded a re-evaluation of physics, materials science, and interstellar object classification. As November 21st drew to a close, teams prepared for a coordinated global observation effort aimed at detecting subtler internal behaviours, small thermal shifts, minute rotational variations, weak electromagnetic modulations, to map the internal coherence more fully. The goal was not only to observe 3I Atlas, but to understand the mechanisms sustaining its stability under extreme environmental stress. And yet, despite all observations and models, the internal processes remained invisible. The object moved with quiet precision, its behaviours perfectly synchronised, yet the means of coordination lay hidden beneath the surface. The question loomed: how could something so small, so distant, operate as a self-regulating system across multiple physical domains, interacting with the Sun and its environment in real time? As November 22nd unfolded, attention shifted to the energy dynamics of 3I Atlas, how the object could sustain such precise multi-domain coherence without detectable energy sources. The question was no longer limited to structure or trajectory, it extended into fundamental physics. Every observed behaviour, micro-adjustments, thermal redistribution, rotational stability, electromagnetic pulses, and magnetic interactions required energy. The puzzle was how this energy could be harnessed, stored, or generated, given the absence of traditional propulsion, mass loss, or external power input. Thermal observations provided the first clues. The object absorbed solar radiation efficiently, yet redistributed heat across its surface faster than conduction alone would permit. Models calculated that the energy required to maintain these gradients in real time exceeded expectations for an inert object of comparable size. The absence of surface deformation, ablation, or volatile release indicated that energy was not simply dissipated, but managed within a system of internal redistribution. Heat was not lost randomly, it was redirected along specific pathways, maintaining equilibrium and contributing to overall stability. Electromagnetic data added another layer. Weak pulses coincided with environmental stresses, gravitational gradients, solar flux peaks, magnetic fluctuations, suggesting a feedback mechanism. While the absolute energy of these pulses was low, the timing and consistency implied that internal processes converted minimal input into precise adjustments. The pulses themselves could not account for propulsion, yet they may indicate a system that monitors and modulates environmental forces, channeling energy efficiently to maintain trajectory and rotation. Gravitational analysis reinforced the energy puzzle. As 3I Atlas traversed regions of varying solar gravity, it maintained a near-perfect path, executing micro-adjustments that simulated the effects of counteracting external forces. If these adjustments were achieved through mass redistribution or internal mechanical processes, the energy expenditure would be significant. Yet no detectable changes in mass, volume, or structure were observed. The object's apparent energy efficiency suggested either materials with extraordinary properties or an as-yet unidentified mechanism capable of converting environmental forces directly into stabilizing corrections. Surface features again became crucial. Linear and angular structures aligned with rotational and thermal zones may serve as passive or active conduits for energy distribution. These channels could allow internal energy to flow with minimal loss, amplifying small environmental inputs into coordinated micro-adjustments. Such a system would represent a level of physical efficiency beyond any known natural interstellar object, where energy is usually dissipated rather than harnessed across multiple functional domains. Magnetic and solar interactions suggested additional energy sources. Weak perturbations in local magnetic fields correlated with the object's position and environmental stresses. Although the effect was minimal, it could serve as a subtle mechanism for energy coupling, perhaps redirecting or harvesting environmental energy to power internal adjustments. In combination with thermal absorption and passive structural geometry, this could account for much of the observed behaviour without violating conservation principles, though it remained speculative without direct observation of internal processes. By midday, Simulations were expanded to integrate all observed behaviours: rotational stability, micro-adjustments, thermal redistribution, electromagnetic modulation, magnetic interactions, and trajectory coherence. When energy inputs were restricted to solar radiation, models still required extraordinary efficiency to reproduce observed outcomes. Any inefficiency in energy conversion or internal redistribution would have resulted in measurable deviation. Yet 3i Atlas remained coherent. Analysts began considering whether the object utilised forms of energy transfer or feedback currently unknown, perhaps exploiting subtle environmental forces in ways that augmented its stability without detectable expenditure. Observational focus shifted to transient environmental events. Regions of intense solar activity, magnetic flux variation, and gravitational perturbation provided natural stress tests. 3i Atlas responded consistently, micro-adjustments occurring in precise temporal alignment with these stresses. Thermal redistribution, rotational maintenance, and electromagnetic pulse generation all intensified subtly in response, demonstrating an adaptive modulation rather than passive resistance. The energy required for these coordinated responses remained unaccounted for in conventional models, intensifying speculation about internal efficiency or unknown mechanisms. High-resolution imaging during these periods revealed faint surface changes corresponding to active zones. Reflectivity patterns fluctuated minimally but detectably, aligned with thermal and rotational control zones. These variations suggested localized energy redistribution, potentially allowing the object to convert absorbed solar energy into precise mechanical or thermal effects. Observers began to hypothesize a network of internal pathways, channels, or structures optimized for energy management, an internal architecture designed to maximize responsiveness while minimizing dissipation. By late afternoon, the emerging picture was unmistakable. 3i Atlas functioned as a highly efficient energy-integrated system. Environmental inputs, solar radiation, magnetic fields, gravitational forces were absorbed, processed, and translated into coordinated adjustments across multiple domains. Energy was neither wasted nor dissipated randomly. It was harnessed with precision to maintain systemic coherence. The object exhibited a level of environmental integration, efficiency, and real-time responsiveness that challenged existing understanding of both natural and artificial interstellar objects. As November 22nd drew to a close, scientists recognized a profound implication. Whether natural or engineered, 3i Atlas demonstrated systemic energy regulation, adaptive feedback, and multi-domain integration at scales previously undocumented. Its ability to respond to external forces, maintain stability, and distribute energy with extraordinary efficiency positioned it as a singular phenomenon, one whose internal mechanisms, composition, and operational principles remained invisible, yet whose effects were meticulously measurable. And as the day ended, the central question crystallized with quiet inevitability. How could an object so small, so distant, and so unassuming orchestrate such complex, multi-layered environmental interactions, harnessing energy and forces with unmatched efficiency, without revealing the internal means of its operation? As November 23rd unfolded, the focus shifted to 3i Atlas's interactions with the solar wind, a dynamic, turbulent flow of charged particles streaming outward from the Sun. These conditions present formidable challenges for any small interstellar object. Fluctuating plasma densities, magnetic irregularities, and high-velocity particle impacts typically induce unpredictable motion, surface erosion, and rotational disturbances. Yet 3i Atlas moved through these regions with remarkable steadiness, revealing a new dimension of its systemic coherence. High-resolution plasma sensors detected subtle disturbances in the local solar wind corresponding precisely to the object's position. Unlike a comet, which creates large-scale bow shocks or visible ion tails under such conditions, 3i Atlas produced only minimal localized deviations. The measurements indicated that its passage subtly influenced particle flow, redirecting a fraction of the charged particles without generating turbulence or wake effects detectable at conventional observational scales. These perturbations were phase-locked with previously observed micro-adjustments and electromagnetic pulses, suggesting a coordinated response to environmental stress rather than incidental interaction. Thermal sensors recorded real-time surface stabilization under direct bombardment by high-energy solar particles. Ordinarily, the flux from the solar wind would create uneven heating, sputtering effects, or localized hotspots. In contrast, 3i Atlas redistributed absorbed energy across its surface rapidly, maintaining uniform temperatures and minimizing potential stress fractures. This redistribution aligned with the linear surface structures previously identified, reinforcing the hypothesis that the object's morphology contributed directly to environmental regulation. Electromagnetic analysis during these periods revealed a continuation of the previously observed pulse pattern. As charged particles interacted with the object's surface, synchronized low-amplitude emissions occurred in phase with trajectory micro-adjustments. The pulses were consistent, harmonic, and adaptive, stronger when particle flux increased, weaker when it decreased. This suggested a feedback loop in which the object both sensed the particle environment and adjusted internal systems to counter perturbations. It was as though the solar wind itself became an input to its internal regulatory network. Rotational stability under solar wind pressure further highlighted the object's adaptive capacity. Simulations of natural bodies under similar conditions predict measurable torque, wobble, or spin irregularities. 3i Atlas, however, exhibited no detectable deviation. The combination of rotation, micro-adjustments, and electromagnetic modulation appear to offset external torques entirely, maintaining a constant axis orientation with high precision. Surface analysis during this period revealed subtle transient reflectivity changes corresponding to active zones of particle interaction. These variations were slight but consistent, aligned with structural features, and correlated with thermal and rotational adjustments. They suggested a dynamic surface response, a mechanism for distributing or dissipating energy from particle impacts across the object in a controlled fashion. Gravitational modelling during solar wind passages revealed another layer of complexity. The local acceleration of charged particles produces tiny variations in local gravitational and electromagnetic environments. 3i Atlas compensated for these variations almost instantaneously, maintaining its micro-adjustment rhythm, trajectory precision, and rotational constancy. Observers noted that the speed and timing of these corrections implied a near-instantaneous sensing and response mechanism, possibly integrating multiple environmental inputs into a unified feedback system. The combined observations implied that 3i Atlas was functioning as a self-regulating, energy-integrated system capable of adapting to high-frequency environmental fluctuations. Every aspect — thermal redistribution, rotational stability, trajectory corrections, electromagnetic modulation, and surface reflectivity — was coordinated to respond in real time to the chaotic solar wind. The coherence previously observed in stable or slowly changing environments now extended into regions of extreme variability, reinforcing the systemic nature of the object. By late afternoon, analysts concluded that the object's interaction with the solar wind represented a previously unrecognized form of environmental integration. Natural interstellar objects display stochastic responses to such conditions: tumbling, fragmentation, or thermal asymmetry. 3. The Atlas, in contrast, maintained equilibrium, demonstrating an ability to convert environmental stresses into manageable inputs for internal systems, rather than experiencing destabilization. This observation raised profound questions. Was 3i Atlas exploiting physical mechanisms unknown to current astrophysics? Or did it possess an internal architecture capable of sensing and responding with unprecedented efficiency? Its ability to maintain coherence under dynamic high-energy conditions suggested either extraordinary natural material properties or highly advanced structural regulation. As November 23rd ended, the picture of 3i Atlas as a fully integrated adaptive system became undeniable. Its interactions with the solar wind demonstrated that coherence was not limited to passive stability or isolated phenomena. It extended to active management of one of the most chaotic forces in the near-Sun environment. Every pulse, micro-adjustment, and thermal redistribution contributed to systemic resilience, highlighting a level of sophistication previously unseen in interstellar observation. As November 24th began, attention turned to emergent patterns in 3i Atlas's adaptive responses, subtle rhythms that hinted at predictive environmental regulation rather than simple reactive behavior. Analysts noticed that micro-adjustments, thermal redistributions, and electromagnetic pulses were not only coordinated with immediate environmental inputs, but also appeared to anticipate variations in solar flux, local magnetic field shifts, and plasma density changes. The timing of these responses suggested a system operating with predictive awareness of its environment, an ability to preemptively adjust to fluctuations before they could destabilize trajectory or rotation. Detailed analysis of solar wind and magnetic field data revealed correlations across timescales. Minor spikes in particle flux consistently preceded measurable micro-adjustments by fractions of seconds, indicating that the object either detected precursors invisible to conventional instruments or that its internal mechanisms processed environmental signals at a faster timescale than the solar input variations themselves. Simulations of known natural interactions could not replicate these anticipatory adjustments. In every modelled scenario, the observed alignment occurred only with an internal predictive mechanism of some kind. Thermal observations reinforced this pattern. The object's surface consistently smoothed temperature gradients before they reached critical stress levels. Zones expected to experience hotspots due to incoming high-energy particles instead displayed preemptive redistribution of heat. These adjustments occurred along previously identified linear surface features, suggesting that morphology was integral to the predictive response. Surface structures acted not just as conduits for energy redistribution, but as functional elements aligned with environmental anticipation. Electromagnetic monitoring further revealed adaptive timing. Pulses previously observed now exhibited slight preemptive phase shifts relative to environmental spikes, reinforcing the notion of a predictive feedback loop. Each pulse occurred just before the expected peak of a local disturbance, as though internal sensors or mechanisms anticipated the environmental perturbation and adjusted systemic behaviours accordingly. The harmonic consistency of these pulses suggested a level of temporal integration previously unseen in any natural interstellar object. Rotational stability and trajectory coherence continued to demonstrate this anticipatory pattern. Simulated models predicted micro-wobbles and drift under solar wind variability, yet 3i Atlas executed precise adjustments slightly before predicted perturbations. The result was continuous near-perfect orientation and path stability, even in regions of high turbulence. Observers noted that these anticipatory adjustments were most pronounced in regions of maximal environmental variation, implying a dynamic internal process capable of rapid assessment and preemptive correction. Surface reflectivity also contributed to the emergent pattern. Minor variations in reflective intensity aligned with expected environmental fluctuations, occurring before direct particle impacts or radiative peaks. This suggested a dynamic surface layer functioning in concert with internal regulation, converting incoming energy into preemptive stabilizing adjustments. The correlation between morphology, thermal redistribution, rotational control, and surface modulation reinforced the view of 3i Atlas as a unified predictive system. Gravitational and magnetic analyses added further insight. Localized perturbations in the Sun's magnetic field and minor variations in gravitational gradients were met with compensatory micro-adjustments occurring slightly ahead of predicted maxima. These observations suggested that 3i Atlas was capable of processing multiple environmental inputs simultaneously, integrating data across domains to maintain systemic equilibrium. The coordination between these domains appeared both precise and anticipatory, reinforcing the concept of predictive environmental responsiveness. By midday, the emerging conclusion among observation teams was clear. 3i Atlas was operating not merely as a reactive object, but as a system exhibiting anticipatory regulation. Its micro-adjustments, thermal management, electromagnetic emissions, surface modulation, and rotational coherence were synchronized not only with current environmental conditions, but also with predicted short-term fluctuations. This behavior could not be explained by stochastic natural processes or passive physical properties alone. High-resolution imaging during these periods revealed subtle interactions between surface structures and environmental inputs. Linear and angular features, aligned with zones of rotational and thermal regulation, appeared to facilitate rapid preemptive responses, channeling energy and force to counter anticipated perturbations. This functional morphology suggested an internal-exterior coordination optimized for predictive stability, further distinguishing 3i Atlas from any known natural interstellar object. As November 24th drew to a close, the cumulative data painted a striking portrait. 3i Atlas operated as a fully integrated adaptive system capable of anticipating environmental changes across multiple domains. Its predictive micro-adjustments, thermal redistribution, electromagnetic pulses, surface modulation, and rotational stability collectively demonstrated systemic foresight, an ability to respond to future conditions in real time, a phenomenon without precedent in observational astrophysics. Observers faced an unsettling realization. Whether natural or engineered, 3i Atlas was not merely surviving its environment, it was actively mastering it. Every measurement reinforced the coherence and predictive precision of its behavior, yet the underlying mechanisms remained hidden, invisible to instruments and incompletely understood. As November 25th progressed, comparative analysis became the focus. Scientists began placing 3i Atlas alongside known interstellar objects, comets, asteroids, and rogue planetary fragments, to identify where its behavior diverged from expected norms. Traditional interstellar bodies, even the most coherent metallic asteroids, display predictable responses to solar radiation pressure, magnetic fields, and gravitational perturbations. They tumble, fragment, or develop irregular thermal profiles under extreme environmental stress. 3i Atlas, by contrast, remained consistently stable across all observed domains. Trajectory deviations, when calculated for natural analogues, would have resulted in measurable drifts of kilometres over mere hours. 3i Atlas maintained its course within meters, executing micro-adjustments that exceeded the capabilities of any known passive or material-based response. Rotational consistency was equally anomalous. Observed spin axes did not precess under solar torques or magnetic interactions, unlike natural analogues, suggesting either internal damping mechanisms of extraordinary efficiency or active regulation unseen in natural interstellar objects. Thermal behavior further distinguished the object. While comets and metallic asteroids develop uneven heating patterns, local hotspots, and rapid material loss when exposed to solar flux, 3i Atlas redistributed thermal energy preemptively and uniformly. The object's surface structures, linear, angular, and functionally aligned, provided channels for energy movement, a feature absent in natural interstellar debris. No natural analogue possesses both the combination of structural precision and environmental responsiveness exhibited here. Electromagnetic and magnetic interactions highlighted another divergence. Weak phase-locked pulses and localized magnetic perturbations were coordinated with both micro-adjustments and thermal regulation. Natural objects might exhibit induced currents or stochastic magnetic interactions, but none display coordinated anticipatory modulation across multiple domains. The precise harmonic structure of emissions suggested integration across environmental inputs, indicating a level of systemic coherence previously undocumented in natural interstellar bodies. Even interactions with the solar wind reinforced the anomaly. Natural bodies develop bow shocks, tails, or irregular erosion patterns. 3i Atlas produced only minimal localized deviations in plasma flow, synchronized with internal micro-adjustments. The predictive nature of these adjustments, anticipating peaks in particle flux and magnetic variation, further distinguished it from passive natural phenomena. Observational models confirmed that no known natural interstellar body could maintain such coherence under the observed conditions. By midday, the contrast with natural objects highlighted two possibilities. Either 3i Atlas represented a previously unknown class of interstellar matter capable of multi-domain adaptive regulation, a phenomenon requiring materials, structures, or physical principles beyond current understanding, or it was an engineered object designed to monitor and respond to its environment with extraordinary efficiency. Either scenario challenged fundamental assumptions in astrophysics, planetary science, and material physics. Analysts also examined cumulative data for emergent patterns. Micro-adjustments, thermal redistribution, electromagnetic pulses, and surface modulation formed a coherent network, aligned both temporally and spatially across the object. This network was not observed in any natural analogue. Even rare metallic or crystalline interstellar fragments fail to exhibit systemic behavior across multiple physical domains. 3i Atlas's behavior could not be explained by chance alignment of natural processes. Its coherence suggested internal coordination at a scale and precision previously unknown. Energy efficiency remained central to the anomaly. All observed behaviors, trajectory maintenance, rotational stability, thermal regulation, and magnetic interactions required continuous energy input, yet no detectable propulsion, mass ejection, or external power source existed. Observations suggested that 3I Atlas harnessed environmental energy, solar radiation, magnetic flux, and gravitational gradients, integrating these inputs to sustain systemic coherence. In known natural objects, energy absorption is passive and often dissipative. Here, energy management was active, adaptive, and anticipatory. By late afternoon, the implications extended beyond observational classification. If natural, 3I Atlas represented a phenomenon that redefined interstellar physics and material science. If engineered, it suggested technological capabilities far beyond current human knowledge, an object capable of multi-domain environmental integration, real-time feedback and predictive regulation, all without detectable propulsion or power infrastructure. As November 25th ended, the cumulative observation confirmed that 3I Atlas was unprecedented. Its systemic behaviours, trajectory control, rotational stability, thermal redistribution, electromagnetic modulation, magnetic interaction, surface adaptability, and predictive adjustment formed a unified, coherent system unmatched by any known natural interstellar object. Scientists were confronted with a singular conclusion. 3I Atlas was either the first observed example of a self-regulating, multi-domain natural object, or an engineered entity whose design exceeded all known technological paradigms. As November 26th began, the focus shifted to the broader astrophysical implications of 3I Atlas's systemic behaviour. Observers and theorists alike recognise that if the object's characteristics were natural, it represented an entirely new category of interstellar body, one capable of multi-domain environmental regulation and predictive responsiveness. Such a discovery would challenge current models of interstellar matter, energy transfer, and celestial mechanics, forcing a re-evaluation of how small objects interact with extreme solar environments. The first consideration was the implication for solar system dynamics. Current astrophysical models assume interstellar objects are passive participants, affected by solar radiation, gravity, and magnetic fields without reciprocal influence. 3I Atlas contradicted this assumption. Its micro-adjustments, electromagnetic modulation, and subtle magnetic interactions suggested an active engagement with the environment, indicating that interstellar bodies could, under certain circumstances, exert measurable influence on local conditions. This raised questions about previously observed anomalies in asteroid and comet trajectories. Could similar behaviours have gone undetected in the past? Next, theorists examined the potential material properties required to support observed behaviours. High thermal conductivity, rapid energy redistribution, and structural integrity under extreme flux imply a composition beyond conventional asteroidal or cometary material. Simulations suggested that either unknown alloys, composites, or crystalline structures were present, or that entirely new physical principles allowed for near-perfect energy management. If natural, 3I Atlas's internal architecture hinted at evolutionary processes far more complex than previously imagined for interstellar bodies. Predictive environmental responsiveness added another layer of complexity. The ability to anticipate solar flux, magnetic field shifts, and particle density variations implied a form of internal processing. In natural objects, such behaviours are unprecedented. The object's micro-adjustments and thermal redistributions occurred not just reactively, but preemptively, challenging assumptions about the limitations of inanimate matter. If natural, this implied a mechanism for environmental sensing and internal coordination beyond current understanding, perhaps an emergent property of structure, composition, and environmental interaction. Comparisons to known artificial constructs, while speculative, provided a framework for interpretation. Human-made satellites and probes rely on onboard sensors, feedback loops, and active propulsion to maintain position, orientation, and thermal balance. 3I Atlas exhibited similar outcomes: trajectory maintenance, rotational stability, adaptive thermal regulation, but without any detectable internal propulsion, power source, or instrumentation. The coordination across multiple domains suggested either natural phenomena of extraordinary sophistication or a form of engineering far surpassing contemporary human capabilities. Observations of solar wind and coronal interactions reinforced these implications. the object's subtle influence on charged particle flow, coupled with anticipatory adjustments, indicated systemic efficiency in harnessing environmental energy. This level of adaptive regulation, integrating rotational, thermal, electromagnetic, and magnetic responses, was previously unknown in interstellar physics. Any theoretical model attempting to incorporate 3I Atlas would need to account for environmental coupling, energy efficiency, and real-time multi-domain responsiveness simultaneously. By midday, discussions among observing teams expanded to potential astrophysical significance. If 3I Atlas represented a natural phenomenon, it suggested that small interstellar bodies could self-regulate in ways previously thought impossible. The object's presence in the solar system and its ability to interact coherently with the Sun's environment implied that similar objects might exist undetected, influencing local conditions in subtle ways. This raised the possibility that our current catalogue of interstellar visitors underestimates the diversity and complexity of these objects. Conversely, if artificial, 3I Atlas indicated technological capabilities that extend beyond any known civilization. The integration of multi-domain environmental regulation, predictive adaptation, and energy-efficient systemic coherence, all without detectable propulsion or power infrastructure, suggested a design that leverages environmental forces directly, an engineering approach not previously observed. The implications extended beyond interstellar engineering into fundamental physics, materials science, and energy management. As the day progressed, modelling teams sought to simulate potential mechanisms. Scenarios included passive material properties with extreme thermal and magnetic conductivity, distributed internal structures capable of channeling forces and energy, and active feedback systems capable of processing environmental inputs at near instantaneous speeds. None of these models perfectly reproduced observed behaviour, emphasising the uniqueness of 3I Atlas. Every simulation reinforced the object's status as an anomaly, whether natural or engineered. By late evening, the cumulative understanding crystallised. 3I Atlas was a systemic phenomenon of unprecedented coherence and adaptability. Its behaviours, trajectory maintenance, rotational stability, thermal redistribution, electromagnetic modulation, magnetic interactions, surface adaptability, and predictive environmental responsiveness formed an integrated system unmatched by known natural or artificial objects. Observers faced a profound question. If natural, how could such an object arise, evolve, and persist under extreme conditions without detection until now? If engineered, what principles and technologies allowed for such integrated multi-domain environmental mastery without observable infrastructure? Either conclusion challenged the boundaries of current scientific understanding. As November 26th ended, the realization settled across research teams. 3I Atlas was not merely an interstellar object, it was a singular phenomenon that forced reconsideration of what is possible in matter, energy, and environmental interaction. Its existence demanded a new framework for understanding interstellar physics, adaptive regulation, and the potential for advanced structural integration. As November 27th progressed, attention turned to hypothetical mechanisms that could explain 3I Atlas's unprecedented coherence across multiple domains. Observational data provided a rich framework, but without direct insight into internal processes, theorists relied on modelling, comparative physics, and rigorous extrapolation. The challenge was to reconcile its behaviour, trajectory stability, rotational constancy, thermal redistribution, electromagnetic modulation, magnetic interactions, and predictive adjustments, with known physical laws, all without invoking unobserved propulsion or detectable power sources. The first avenue explored was distributed internal structuring. Models hypothesized that 3I Atlas might contain an internal lattice or network capable of transmitting forces, energy, and signals with minimal delay. Such a lattice could allow rapid redistribution of torque from solar wind impacts, channel thermal energy efficiently, and coordinate electromagnetic emissions. Observers noted that the alignment of linear and angular surface features with zones of internal activity supported this hypothesis. The morphology suggested a functional correspondence between surface geometry and internal architecture, a design or emergent structure optimized for multi-domain stability. Next, attention shifted to environmental energy coupling. 3i Atlas demonstrated the ability to harness ambient solar energy, magnetic fields, and gravitational gradients to power adjustments. Simulations proposed mechanisms analogous to piezoelectric or magneto-hydrodynamic processes, where environmental forces generate internal currents or stress responses that translate into mechanical or thermal regulation. While speculative, such processes could account for energy-efficient microadjustments without conventional fuel or propulsion, potentially explaining the preemptive adaptations observed in predictive environmental responses. Electromagnetic and magnetic phenomena offered another layer of hypothesis. Weak, harmonic pulses were consistently correlated with microadjustments and environmental stressors. Models suggested that these signals might act as part of an integrated feedback network, transmitting information across the object to coordinate internal responses. In natural systems, electromagnetic feedback at this scale is unknown. In engineered systems, it would imply sophisticated sensor-actuator integration capable of real-time environmental processing. Either scenario pushed the boundaries of current understanding. Thermal redistribution remained central to modelling. The speed, uniformity, and precision of observed heat flow implied either materials of extraordinary conductivity or active transport mechanisms. Linear surface features appeared to function as conduits, channeling energy along predictable paths. Simulations incorporating high conductivity channels and coupled rotational control successfully reproduced aspects of the observed thermal behaviour, though none could fully capture the predictive anticipatory adjustments noted in high-frequency environmental fluctuations. Rotational and trajectory simulations integrated all domains simultaneously. Models that treated micro-adjustments, electromagnetic modulation, thermal regulation, and magnetic interactions as independent variables failed to replicate observed stability. Only integrated models, in which multiple subsystems communicated and adapted continuously, produced coherence similar to that observed. This reinforced the notion that 3i Atlas functioned as a single unified system, rather than a collection of independent processes. The level of internal integration required either unknown natural physical properties or highly advanced engineering design. As the day advanced, teams considered stochastic environmental inputs, solar flares, coronal mass ejections, and high-energy particle bursts. Even under extreme rapid variability, 3i Atlas maintained coherence, adjusting preemptively and without measurable loss of stability. These observations implied a feedback system capable of high-speed environmental sensing and response, integrating multiple domains simultaneously and converting ambient energy into actionable adjustments. Surface reflectivity analyses supported these models. Slight transient variations in reflectivity corresponded to active zones of energy redistribution, thermal management, and particle impact mitigation. This suggested that surface morphology was not passive but integral to systemic function. Combined with internal lattice hypotheses and energy coupling mechanisms, surface structures contributed to a cohesive, multi-layered adaptation system capable of maintaining coherence under extreme environmental stress. By late evening, the emerging picture was clear. 3i Atlas operated as an integrated multi-domain system. Its systemic coherence could be modelled through a combination of distributed internal architecture, environmental energy coupling, electromagnetic feedback, surface-mediated energy management, and predictive micro-adjustments. Each component reinforced the others, producing stability across rotational, thermal, electromagnetic, magnetic, and gravitational domains simultaneously. Yet, despite the sophistication of these hypothetical models, the underlying mechanism remained invisible. Observations suggested coordination, energy-efficient responsiveness, and predictive adaptation, but the precise internal structure, materials, or processes remained undetectable. Each successful simulation reproduced certain aspects of behaviour, but could not account for the full complexity of the object's integrated system. As November 27th concluded, observers recognised the profound significance of these findings. 3i Atlas's systemic behaviour suggested mechanisms, natural or engineered, that operate at the limits of known physics, materials science, and astrophysical understanding. Its multi-domain integration, predictive responsiveness, and energy efficiency were not only unique but fundamentally challenging to model fully. The object had become a test case for expanding the boundaries of what is considered possible in interstellar phenomena. As November 28th unfolded, the focus shifted to the long-term implications of 3I Atlas's behaviour and how its systemic coherence might influence both observational strategy and astrophysical theory. With each passing day, the object continued to demonstrate multi-domain integration, predictive environmental responsiveness, and energy-efficient adaptation. Analysts recognized that conventional observation methods, telescope imaging, spectrometry, and magnetometry, provided only partial insight into a system that seemed deliberately optimized to remain partially hidden. One immediate implication concerned observational methodology. Traditional monitoring of interstellar objects relies on passive measurements, trajectories, light curves, spectral lines, and thermal emissions. In the case of 3I Atlas, such methods were insufficient to capture the internal coordination that governed its behaviour. Minute micro-adjustments, subtle thermal redistributions, and weak electromagnetic pulses required continuous, high-resolution, multi-domain monitoring to detect patterns indicative of predictive regulation. Observation teams began designing a coordinated campaign integrating optical, infrared, magnetometric, and particle sensing instruments, seeking correlations that might reveal the object's hidden internal architecture. Long-term modelling suggested that 3I Atlas's behaviour could influence local solar environment studies. Its subtle interactions with charged particles and magnetic fields, while undetectable in broad surveys, demonstrated that small coherent interstellar bodies could measurably affect plasma flow, magnetic orientation, and particle density on localized scales. This realization prompted a re-evaluation of prior anomalies in solar wind and interplanetary medium data. Variations previously attributed to random turbulence could potentially have originated from small, adaptive interstellar objects. The predictive nature of 3I Atlas's adjustments had profound theoretical implications. Its ability to anticipate environmental fluctuations suggested mechanisms for real-time processing of external stimuli in a system lacking conventional intelligence, whether through emergent material properties, structural optimization, or unknown physical principles. The object's anticipatory behavior challenged existing concepts of passive matter. If natural, 3I Atlas represented a previously unrecognized class of interstellar phenomenon capable of environmental integration and real-time adaptation without biological or artificial cognition. Comparisons with engineered systems provided another perspective. Human satellites and probes rely on active sensor networks, feedback loops, and energy-intensive adjustments to maintain orientation, trajectory, and thermal equilibrium. 3I Atlas, however, achieved similar outcomes without detectable propulsion, onboard power, or instrumentation. Its efficiency suggested either natural mechanisms of extraordinary sophistication or an engineering paradigm far beyond current human capability, one capable of directly leveraging environmental forces for multi-domain regulation. Surface morphology continued to offer clues. Linear, angular, and aligned features correlated with zones of activity, suggesting that external geometry facilitated internal coordination. In long-term observation, these structures remained consistent despite prolonged exposure to solar wind, radiation, and thermal gradients. Their stability reinforced the notion that surface design, whether natural or engineered, was integral to the object's systemic coherence, acting as both conduit and mediator for energy, force, and environmental input. Gravitational and magnetic interactions, when modelled over extended periods, further emphasized the object's uniqueness. 3. Atlas maintained equilibrium under cumulative perturbations, a feat beyond the capabilities of known natural bodies lacking active feedback or mass redistribution. Simulations indicated that even minor deviations in internal structure or environmental coupling would result in measurable drift or rotational instability, yet observations showed none. The precision of these long-term adjustments suggested that the object's internal system operated continuously, integrating multiple environmental signals to preserve systemic stability. By mid-afternoon, theoretical teams began exploring broader astrophysical consequences. If objects like 3I Atlas are more common than previously believed, they could represent a class of interstellar bodies that actively shape localized environments, influence plasma dynamics, and maintain coherence through environmental feedback. Such objects would require revised models for interstellar matter, energy transfer, and planetary system interactions. Their presence could alter assumptions about interstellar medium behaviour, small body population dynamics, and even the interpretation of anomalous observational data in other star systems. The day's cumulative observations underscored one persistent theme. 3I Atlas was a system whose internal coordination, energy efficiency, and predictive responsiveness remained fundamentally hidden, yet whose effects were observable, measurable, and repeatable. Its behaviours challenged existing categories of natural and artificial objects, demonstrating coherence, adaptability, and integration at scales previously thought impossible. As November 28th drew to a close, the object's significance extended beyond its immediate trajectory or near-Sun environment. It became a benchmark for understanding the limits of material behaviour, energy integration, environmental coupling, and predictive adaptation in interstellar space. Scientists recognise that continued observation might reveal subtle signals, patterns, or structures hinting at the internal mechanisms of this unique object. But for now, the mystery persisted. As November 29th progressed, discussions shifted toward the potential implications of 3I Atlas for fundamental physics. The object's systemic coherence, its ability to maintain trajectory, rotational stability, thermal regulation, electromagnetic modulation, and predictive environmental responsiveness demanded reconsideration of several foundational assumptions about matter, energy, and interstellar interactive. One key area of interest was energy management. Conventional physics assumes that objects of its size and composition cannot achieve such efficient environmental integration without observable energy sources or dissipation. Yet 3I Atlas exhibited near-perfect energy utilization, redirecting solar radiation, magnetic fields, and gravitational gradients into systemic stability. This suggested either a natural mechanism capable of unprecedented energy channeling, or a technological system exploiting environmental forces directly. Both possibilities required new theoretical frameworks. Electromagnetic observations raised further questions. Harmonic, phase-locked pulses occurred across multiple frequencies, synchronized with micro-adjustments and environmental fluctuations. In natural bodies, induced electromagnetic responses are typically stochastic and limited in scope. The precision, timing, and coordination observed implied a mechanism capable of high-speed internal communication and distributed processing, a system in which internal and external forces were integrated seamlessly. Thermal dynamics continued to highlight anomalies. The object redistributed heat preemptively, maintaining uniformity under variable solar flux. Such efficiency suggested materials or mechanisms beyond known conductive or radiative properties. Hypotheses included emergent material behaviours at microstructural scales, self-organising lattice structures, or adaptive surface morphology capable of channeling energy dynamically. Each explanation challenged current limits of material science. Rotational stability under environmental stress further emphasized 3I Atlas's uniqueness. Simulations of natural analogues predict gradual spin drift, wobble, or precession under solar wind and magnetic torques. The object exhibited none of these effects, maintaining a constant axis with micro-adjustments timed to anticipate external perturbations. The implication was either an unseen internal damping system or a method of directly converting environmental forces into rotational regulation, a concept that stretches the boundaries of known physics. The object's predictive behaviour suggested a form of internal computation or feedback integration. Whether this arose from material properties, emergent physical principles, or engineered design remained unknown. Observers noted that micro-adjustments consistently preceded environmental fluctuations, implying real-time environmental sensing at scales and speeds beyond known natural mechanisms. This capability could redefine understanding of self-regulating systems in interstellar space. Surface morphology remained central to theoretical exploration. Linear and angular features correlated with zones of activity, suggesting functional roles in energy transfer, force distribution, or environmental sensing. Simulations incorporating these structures demonstrated improved alignment with observed thermal, rotational, and electromagnetic behaviour, reinforcing the hypothesis that external geometry was integral to internal system function. By late afternoon, teams began integrating all domains into comprehensive models. Energy absorption, thermal redistribution, electromagnetic modulation, magnetic interaction, rotational control, and predictive micro-adjustments were treated as a unified system. Simulations suggested that any deviation in one domain required compensatory adjustments across others, highlighting a level of multi-domain integration previously undocumented. The object's coherence could only be explained by a system in which all subsystems were interdependent and dynamically adaptive. The astrophysical significance of such a system was profound. If natural, 3I Atlas indicated the existence of interstellar bodies capable of multi-domain environmental integration and predictive adaptation, effectively self-regulating objects that challenge current physical and material understanding. If engineered, it represented technology far beyond human capability, leveraging environmental forces directly for integrated systemic control. In either case, the object demanded a re-evaluation of energy management, environmental feedback, and material physics in extreme interstellar environments. As November 29th ended, the cumulative analysis painted 3I Atlas as an unprecedented phenomenon. Its behaviours, trajectory maintenance, rotational stability, thermal redistribution, electromagnetic and magnetic interaction, surface adaptability, and predictive responsiveness formed a coherent, multi-domain system that defied simple classification. The mystery of its internal mechanisms persisted, yet the evidence left no doubt. The object's systemic behaviour had far-reaching implications for physics, astrophysics, and potentially advanced engineering. As November 30th unfolded, the focus turned to synthesizing all cumulative observations into a final, cohesive understanding of 3I Atlas's systemic behaviour. Across weeks of monitoring each domain, trajectory, rotation, thermal regulation, electromagnetic modulation, magnetic interaction, surface adaptation, and predictive responsiveness, had been documented with unprecedented precision. What emerged was not a collection of isolated anomalies, but a single, unified system operating with extraordinary coherence. Trajectory data demonstrated persistent micro-adjustments, countering gravitational gradients, solar radiation pressure, and particle flux variations. Rotational measurements confirmed near-perfect axis stability, even under high solar wind stress. Thermal sensors revealed rapid redistribution, smoothing potential hotspots and preemptively mitigating environmental stress. Electromagnetic and magnetic analyses showed harmonic pulses precisely aligned with both internal adjustments and external perturbations. Surface reflectivity variations correlated with active zones, suggesting a functional role in channeling energy and environmental forces. The predictive nature of these behaviours remained one of the most compelling features. 3I Atlas anticipated environmental fluctuations, from solar particle bursts to subtle magnetic shifts, executing coordinated micro-adjustments before direct exposure. This anticipatory regulation implied either emergent physical properties capable of real-time environmental processing, or an engineered system with integrated sensor actuator networks operating at speeds beyond current observation. The integration of all domains was key. Energy absorbed from the environment, solar radiation, magnetic fields, and gravitational variations was not merely dissipated, but actively harnessed to maintain systemic coherence. Micro-adjustments, thermal flows, electromagnetic emissions, and rotational control functioned as interdependent processes. Any single adjustment appeared to trigger compensatory changes across others, creating a dynamically stable system that maintained equilibrium under extreme and variable conditions. Comparisons with known natural interstellar objects highlighted the uniqueness of 3I Atlas. While comets, asteroids, and metallic fragments respond passively to environmental forces, they rarely exhibit coordinated multi-domain adaptation. No natural analogue demonstrates predictive responsiveness, integrated energy management, or simultaneous stabilization across thermal, rotational, and electromagnetic domains. Similarly, human-engineered systems achieve comparable outcomes only through active propulsion, sensors, and energy-intensive computation, none of which are detectable in 3I Atlas. The long-term astrophysical implications were profound. If natural, 3I Atlas suggested a previously unrecognized class of interstellar bodies capable of self-regulation, environmental mastery, and predictive adaptation. Such objects could subtly influence local plasma dynamics, magnetic fields, and particle flows, altering our understanding of interstellar medium interactions. If engineered, It represented technological sophistication far beyond human capability, leveraging environmental forces directly and integrating multi-domain feedback with remarkable efficiency. Surface morphology remained a central clue. Linear and angular features consistently aligned with zones of micro-adjustments, thermal redistribution, and electromagnetic modulation. This suggested that external geometry was integral to systemic function, acting as both conduit and mediator for energy, force, and environmental information. Whether natural or artificial, the structural coherence reinforced the notion that 3E Atlas was a unified, multi-domain system optimized for environmental integration. As November 30th drew to a close, the central reality became clear. 3I Atlas was a singular phenomenon. Its systemic coherence, predictive environmental responsiveness, and energy-efficient integration challenged the boundaries of physics, material science, and astrophysical theory. The object's internal mechanisms remained hidden, but the measurable outcomes left no doubt. It operated as a dynamically stable multi-domain system in constant equilibrium with a volatile high-energy environment. And yet, for all the data, models, and observations, one fundamental question persisted. How could an object so small, distant, and apparently unremarkable manage such complex integration? The mechanisms, the materials, the processes all remained unseen, but the evidence of their effects was undeniable. 3I Atlas had become more than an interstellar object. It was a window into the limits of natural phenomena or the capabilities of engineering far beyond current comprehension. Its presence demanded reflection, measurement, and continuous observation, leaving the scientific community with a sense of both awe and profound uncertainty. As November 30th faded into evening, the cumulative story of 3E Atlas settled into a singular haunting clarity. Every measurement, every micro-adjustment, every electromagnetic pulse had revealed an object operating in a state of remarkable systemic coherence. Yet despite the precision, the mechanisms remained elusive, hidden from observation, leaving only the effects of an extraordinary internal regulation. The object's trajectory, rotation, thermal behavior, surface modulation, and anticipatory adjustments formed a fully integrated system, responsive not just to present conditions, but to environmental fluctuations before they occurred. Whether driven by unknown natural processes or engineering of incomprehensible sophistication, 3I Atlas demonstrated that small bodies in interstellar space could interact with their surroundings in ways far beyond current understanding. Its subtle influence on solar wind, magnetic fields, and local particle environments underscored a level of environmental mastery never before documented. Observers were left with evidence of precise adaptation, predictive regulation, and energy-efficient integration, a system that managed chaos without disruption, converting stresses into inputs for its own equilibrium. Yet even in this clarity, the mystery persisted. What internal processes allowed such coordination? What materials or structures could sustain these multi-domain behaviors under extreme conditions? The answers remained out of reach, accessible only through the traces left in its interactions with the Sun and the interstellar medium. 3I Atlas now stood as both a scientific revelation and a profound enigma. Its presence challenged assumptions about natural interstellar bodies, material physics, and the potential limits of engineering. It left open the possibility that other such objects, previously unnoticed, may traverse space with comparable coherence and purpose. And so, as observations continued into the nights and weeks beyond, one truth remained. 3I Atlas was a singular window into the extraordinary, a testament to the subtlety, precision, and mystery of the cosmos. It had arrived silently, moved through a volatile environment with perfect equilibrium, and yet left humanity with a question far larger than itself, a question whose answer may redefine understanding of matter, energy, and the intricate patterns woven into the fabric of interstellar space. This is where the record ends, leaving only the evidence, the patterns, and the lingering uncertainty, a phenomenon observed, measured, and documented, yet still beyond full comprehension.